earlier? Oh. How's fellowship?
It's doing really well.
Like it?
Yeah, it's fun.
Yeah, it's a lot of work, but it's fun.
Yeah, it's a lot busier than I expected.
Yep. Yeah, exactly. Yeah. I used to think that I will have more free time, but not really.
No, not at all. Yeah.
No. I'll get, I think, easier like when you're a senior.
Yeah. Bit more free time then.
Yeah. Are you like teaching every Saturday or like?
This is my first CSM.
Oh, really?
Yeah. Yeah, I think we got divided up pretty evenly. I don't know if anyone has more than one.
I ended up not having any CS Saturdays. I did like the after hours boot camps.
Boot camp prep. Yeah, I'm doing a lot of boot camp prep.
Yeah. It's like, but then I ended up with days that I had like a lot of extra off days and time off, and I never took them.
Yeah, I have a feeling I'm gonna end up doing that.
Yeah. Oh, they have a picture of a dog there? Today? Really?
Oh yeah. Is it Jaren still?
I don't know.
Well, there's Cooper and there's also Beck.
Who's Cooper?
Cooper's a golden retriever who belonged to people who were in the class ahead of me. They were fellows, and they brought him all the time. He was his dog, and I loved him. But yeah, obviously he hasn't been here in a while.
Yeah.
But he is still alive in the hearts and emojis.
No, there's like another one, I think, too.
Yeah, that's Beck.
Really? Oh yeah, it is Ben. Yeah, Cooper's picture is like huge. I could see it from there. Are you guys doing React?
Yeah.
How's that?
We haven't started it yet. They have their express equalize checkpoint on Monday. Juke React is good. I'm like halfway through it.
Hey Tom, can we have access to the Juke React or no?
I think it's made available to everyone. They sent it to my class's flight in 1607.
Oh really? They did?
They put it on LearnDoc for all of them, yeah.
I don't know if we've done that yet. I think we are going to do it. David has like an idea for how he wants to do it. But right now we're kind of like we're kind of like iterating on them a bit. And parts 1 through 3 are done, but parts 4 through 5 we're still being worked on.
Yeah. I think the older version of it is still available to our class.
Yeah, you can still, the older version is still available.
Yeah.
But the newer one, which I think will be better,
Yeah.
still not.
How are you handling everything with the React? You were like the busiest when they started rolling it out.
Yeah. Like I've done parts 1 through 3. Leave it. And Joe's going to do parts 4 and 5. Hello, testing. Hello. Parts 1 through 3 are a pretty better approach.
Oh, interesting.
Yeah, he's been React forever, and the order is better now.
Yeah, it's hindsight 2020.
Are we doing like? Are you guys doing with Redux, like introducing React and then Redux,
Yeah,
or are you doing it all together?
React and then Redux.
Yeah, it's like I'll do we'll do like 3 days of React now and then Redux and then React Redux.
Oh, interesting.
I will in a few minutes.
YouTube, is this coming through?
Test. Is this fine, Elliot? Am I good? Okay, or should I put it? Put it closer. Okay. Is it good? Should I speak louder? Should I speak louder? Okay. Hi, Chris. What's up?
Hey, New York, and good morning, remote. Some messages for you. The fire alarm is going to be going off all day, so I apologize about the noise we're going to be getting all day. Don't get concerned. The building is not on fire. And then this is Ani. She was a fellow
Hello.
here, and she's going to be talking to us about her experience at a VR hackathon at MIT.
Thank you. Hi, everyone. I'm Ani, as Elliot said. I'm a full stack alum. And I'm here to tell you about the hackathon experience that I had at MIT. Has anyone been at the hackathon? Like,
I haven't participated.
oh, okay. So the one thing, if like during my presentation you have questions, please go to the microphone because we want the remote students to hear you guys too, and then I'll be happy to answer anything. So if you walk to the microphone, I'll know that you have a question. So feel free. So yeah. So hackathons are fun. I don't know. Like I've been to few, and the one that I'm going to share with you is the one I went to at MIT. I went there with my friend. Friend Julia, she is another full stack alum. She graduated actually after me, and she cannot be here because she's back in Germany. She's originally from Germany, so she came to do the boot camp and she went back. So so we registered and we went to Cambridge. I'm gonna show you the website. It was in the beginning of October. All right, so the hackathon was 3 days. It started on Friday, and then they had the prizes, and like on Monday they would tell the winners, and then the prize distribution was on Monday. So it was like almost like full 4-day event. The whole Friday was like registration in the morning, and then they had workshops. And I tried to attend as many as I could, but it was a lot of like workshops. So Google brought their Daydream. Has anyone ever played with any VR or AR gadgets? Yes.
Yeah, I played with my friend has the View, I think it's called. It's got like 2 little controllers, and it's like a VR experience where you're in like a 6-foot box and you can move around and you can.
Yeah. Okay. So he wears the glasses.
Yeah.
Yeah. Okay. Yeah. So that's pretty much like you have this big goggles or like huge, and then you like most of them are like that. Or you can use actually your phone and use Google Cardboard, which kind of look like this, and those are like simpler version of web VR. So yeah, and I had very little knowledge of what about augmented reality or virtual reality technologies, and I thought, well, this is going to be a cool experience. I will learn a lot because they had like mentors and all the companies presented their gadgets there. So I'm gonna show you some pictures from there. So they fed us, of course, the food. That was very important. They had breakfast, lunch, and dinner. So okay, this is the team that the volunteers and organizers. And oh, this is like prizes. Hold on. Something wrong is with this at the end. Let me start from the beginning. Looks like it's not sorted, but okay. So this is during the hackathon. I cannot see myself, but I was here. This is like one of the rooms. They had like two big rooms where people teamed up and they were hacking all day, like 2 days. And most people were doing trying to build something with Unity. Unity, it's a platform where you write with Java or C# or C++, I believe. And I went there without like really like having experience with Unity, and I thought, well, during 2 days I'm not gonna really learn much, and I won't be able to build much. Can I really use like JavaScript knowledge that I learned here at the bootcamp there? So I asked one of the organizers, and he said, well, you can create web VR with JavaScript, and there's a framework called A-Frame. And that's what we ended up using because I wanted to use my recent knowledge and then see what I can build with it. So yeah, this is, let me see if I have a picture. Those are the workshops. This was they had workshops for Unity. I tried to install and play around, and I understood that within a day, I won't be able to accomplish too much. This is the food. Yeah, it was really good. I mean, it was very well organized. They made sure that everyone is fed and happy. So so the way they divided the teams, they divided us Friday night, evening. They divided us into groups depending in which area you want to hack, what you want to build. Mostly it was healthcare, I think, and then media and entertainment. I think there were 2 more. I can't remember. And then within your group, if you had an idea, you would pitch it and then see if other people want to join your team. We had one more person joining our team. With my friend, we decided to have our own small team, and then one more person joined us. Let me see if I can find a picture. Yeah, okay. Okay, this was my team. Yeah. So we built, so what we wanted to build web environment where you can collaborate with your friends, kind of hang out in your own picture and then talk about it and discuss it. Originally, idea was to create kind of escape room, but we kind of pivoted from it and wanted to do something more like a social thing where you can upload a picture and then just talk about, discuss it, or do something. And this is what we came up with. All right. So let's say this is a picture. You're here, and then you can see, and then we had a chat. You guys actually can go online and join the chat, and you can chat. So you have to all log in with your Facebook we're not taking any information from you, so all you have is like it takes just your name and you can chat, and it's like it's real time. So let's say hold on. Didn't go through. Okay. All right, so it works. Okay. So if I refresh this, it's still gonna work. Okay. So yeah, so you can see like 360, the picture, and then if you click, oh, I clicked it already. So if you change something on one, on your side, it will change for the other person too. So this is like really like all we could get working. We got, I don't know, I don't think you played with sockets yet. Oh, okay. And so we used sockets to have this communication, like real-time communication between two clients. And we used Firebase. It's a database for the chat. It's a database that persists your chat messages. And it's like it pushes the changes to the other client. So that's like how the chat works. And we used Angular. You guys are not going to learn Angular. We're going to do React for the front end. But it's like a different framework that we used. So you can, if you go to another picture, so it's a different chat. So you can do stuff here. It's like it's on its own. So let's say here. And this is the option if you want to use on your phone. If you open this in the phone and then click this, you can actually use that with those glasses and just like look around. It will work. So if like later you want to try out, just stop by. You can try this. I thought to give you like a small presentation of how like A-frame works, the code, to show you how it works. And let me change this. I don't need this. I don't need this. All right. All right, so this is like a simple example, kind of like a hello world for A-frame. And I'll show you how the code looks like. All right, this is all you have for the front end, like for client side. You have to have the embed the A-frame. This is like the actual library. And those are the tags that are responsible for all the objects in here. So let's say, let me close the sky quit. Right. Right, let me put this on the side. Okay, let's say I want to change something here. I want to change color. Have this black. Yeah, so it will change the color to black. It's pretty easy. And to have the actual 360 picture, you can just simply have you need to have 360, like the JPEG, the actual picture, and then you add it to your A-frame like this. You just add the source to it, and then it will add to the background. Like you can see this. Another cool thing you can do, you can actually add this to your objects. The background as a picture, for example, to your box. I have another one too. Okay, this will add the texture to the actual box. So you can move things around. I didn't add that functionality for this boilerplate for the example, but yeah, you can move things and then do other like animations and stuff. So it's really cool framework. I really liked it because like I had no idea how things work and was able to figure out within a day just the basics to have something working for the hackathon. That's actually what you want. You want to put something together very fast. So. That's pretty much about what we've done. Yeah. Questions? Can you? Yeah.
Hopefully this will work. How do you? So when you're at a hackathon in general, not just doing something with like VR, how do you balance doing something ambitious but that has like a 75% chance of failing and you end up with nothing, versus doing something that's a little more bounded? Where you're more likely to end up with something to present at the end?
I suggest to go with ambitious one, because even if if you try to have something working, it's better than to go something with like 100. It's because it's a hackathon. They understand that it's not going to be. It's going to be buggy. Like for our project, it was like we could move things, but it was not propagating to other clients. Now when I try it, I cannot even move. I don't know, it broke. So it changes the color, but I cannot move it anymore. I don't know why, because I have to look into it. I didn't really touch the project since the hackathon. But go with ambitious because I've seen other projects, like other people, but they build with Unity. A lot of like people build with that, because like people travel from different countries to come to that hackathon. And they came with their own equipment too. So it was very like, I met a lot of like really like smart and like ambitious and like interesting people. It was fun. And yeah, some of the projects are like, some people built like for kids, to a playground for kids in pediatric hospital where they cannot really communicate with kids, but they can have a common area where they can play. And I've seen a storytelling app too. So they would type, for example, once upon a time there was a princess and dragon, and it will appear right there, like in 3D on the screen. So, and you can see like in Google Glasses or VR Glass. So it was like very cool. Yeah. So go with ambitious. I mean, you can pivot later, like see, okay, this is like maybe we want, but you want to have to show, you want to be able to show something that works, even if it's like half done. Any other questions? Yeah.
Is there anything that you wish you'd known or been prepared for going into it?
Yes. So I've been to probably only 3 hackathons so far, and it's good to do more research about the companies who sponsor hackathon and technologies that are going to be used. So, and then have some boilerplates for your initial setup, because it took me some time to set up the server and the backend, which is not essential for the actual hackathon, but it takes a lot of time to make it work. So go prepared and go. It's good to go with one person at least, with you, a friend, and then you can recruit other people. And try not to go, not to have a team more than 4 people. 4 or 5 people is because then it gets harder to manage the team and divide the work, because you don't really have time to do a lot of planning. So you want to have get there and coding. It's good to have a designer in your team and developers. So that's it will be a good combination. I wish I knew A-frame before I went there, so I didn't spend time learning it right there. but it was fun, and like I realized it's not that hard, but it's very, very doable. Anything else? Yeah, go to Hackathon. They're fun. Especially, they feed you. They have mentors. They they were very supportive. Like I think this MIT Hackathon was very well organized because so originally our team was like we had a person, then she could not come, and then another person joined later, like the third person like on a picture, he joined later, and like halfway through on Saturday. So it helped a lot because like we were running really behind, and you never know. Maybe someone is like will not be able to make it. Something happens, and then we went to the organizers and I told them, and I was like about to like give up and go home, and he's like, no, it's like you just slack and say that you need one more team like member, and then like I slacked it and someone joined. So it's like just go till the end.
Sleep did you get while you were back?
Not a lot. But they did encourage. They said, go home. They didn't let us stay there like overnight. They kicked us out from the building. They're like, you can code if you want to, but we don't, like, just get some rest. Because at the end you get like something, like it's very close to the like pens down when you have to like submit your code. And you find out that you have so many bugs, nothing is working, and then you get frustrated. So if you're like rested, it's like it's easier to handle this situation. So, all right, I guess good. Anyone, if you want to try, come stop by. I'll be happy to show you.
A little bit more? Or what? S'more. S'more what? Cool, we're good? All right. Uh-oh. Cool. Hey, welcome everybody. Thank you for coming out to ASCS Saturday, even though it is a fairly nice day outside. You have chosen to hang out with me instead and learn about functional programming and the way that Git works internally. So before we get started, I'm just going to remind you that we have a very special guest today, my friend Mike. So Mike is there in the center. And Mike really wants to hear all of your questions because we have our remote listeners as well. So we want them to hear your questions too, because I'm sure that they are wonderful and intelligent questions. And Mike is really curious. If you don't talk to Mike, then I will be offended that you are not talking to my friend and will promptly ignore you. So please, if you have a question, make sure to tell Mike. Awesome. Cool. So the first thing we're going to talk about today is we're going to talk about immutable data structures. So we are going to be talking quite a bit about Git a little bit later. But really, I think the main thrust of this CS Saturday is really about functional programming and immutability. And Git, as we'll see, is really one of my favorite examples of an immutable data structure that implements a really functional structure to the way that it's organized. And it's really cool. It will make more sense as we get into it. Cool. So essentially, here's the schedule for today. It's about 11 o'clock now, so we're going to lecture till about 12, in which then we'll start a workshop in which you're going to be implementing a immutable linked list. Then we'll do that until lunch,
and then when we get back, we'll do a review, and then we will start the workshop, we'll start the lecture on Git internals, and then do a workshop called FVS, our full stack version system, potentially also functional version system. Also, if you have a really clever like pun name, like off of Git or something that we can use for this, then please let me know, because FVS, I've never been super satisfied with this name. I really want something cute and clever, and I've never been able to come up with anything. But essentially, it's going to be a small little version of Git that you can, in fact, use yourself. I just wouldn't recommend it, because it's not going to be as good as the real Git. But it will work. It will be cool. But cool, so let's go ahead and let's get started. Cool, so functional programming. It's kind of this nebulous term that you probably hear bandied around a lot, especially in the JavaScript world these days. But what exactly does it mean? How do we think about it? The way that I like to think about it is that it's a programming paradigm, in the same way that we think about object-oriented programming as a paradigm. So at this point, object-oriented programming is very popular. Programmers have been using it for years, so there's a set of ideas around it that are very concrete. So if somebody were to ask you, what does object-oriented programming means, we would immediately start saying things like, okay, you have classes that have instances of classes, and there's inheritance and encapsulation and polymorphism, all these sorts of things. Functional programming is very similar to that. It's sort of this collection of ideas that is a little bit nebulous, but once you so really they're more like just like the features of a paradigm rather than necessarily a strict definition. A good way of comparing it, if you're going off of the object-oriented paradigm as your basis, is that in object-oriented paradigm, our main unit of computation is this object. It has behavior, which we call methods, and it has attributes, like its properties. When we might think our main unit of computation, if we're talking about dogs, is going to be like a dog that has a name and a breed and an age and all of that wonderful stuff that we did like on code school like a long time ago. It has methods like barking and saying its name. We've built it a million times. Functional programming is a bit different in that our main unit of computation is going to be a function. And probably the most special thing about these functions that we're going to write when we're writing in a functional paradigm is that they're going to be pure functions, which means that they must produce the same output for the same input. Don't worry, we're not actually on fire. So we'll see a little bit more about the features of the functions that we want to write when we're writing in a functional style. Cool. So when we're writing in a functional style, here are sort of the things that we're going to get. Here are here's what we would expect if we're writing with functional programming appropriately. The first thing we're going to expect is that our code is going to be very predictable because we're writing these pure functions that are always just going to do simple calculations, like just returning the same output for the same input. That means we're always going to be able to predict what we're going to get from our program based on any input that we give it. There's not going to be like any surprises or side effects that are going to be contingent upon anything except for the input. So that's something that we all really want as developers. And that's something that can be really difficult when you're programming in an object-oriented paradigm where you have these objects that maintain internal state and mutate each other, because then what you get out of the program is going to be contingent upon the internal state of all these objects at any point in time. But with a functional program, what you're going to get is always just going to be the same depending on what you put into it. Some other features that you might think about with functional programming is this concept of composability. So we've touched upon this quite a bit in Foundations as well, I believe, where you've written functions that return other functions or functions that like wrap other functions with their own functionality before giving them back to you. That's something that we would say is a feature of functional programming. And it's something that JavaScript is really good at because functions in JavaScript are first-class citizens. You can pass them around as values. You can like mix and match them. They're really flexible. And it's not something that can happen all the time with languages that tend to be more object-oriented based. Recursion is sort of like the hello world in functional programming land. So like, for example, if you're learning a language like Haskell, instead of like writing a simple dog class or something to say hello, you might instead do something like the Fibonacci or something like that, just because recursion is just something that's so like, it's almost like a little bit like like fashion. I guess like it's it's such a functional thing. It's so based around this idea of functions layering on functions. So writing in a recursive style tends to be something that will come out a lot of functional programming. This last feature is, which we're going to focus on quite a bit more, is this idea of immutable data structures, which essentially means that when you're storing your data, you're storing it in such a way that once you create the data, it cannot be changed afterwards. So let's see what that looks like a little bit more. So immutability. State cannot be modified after creation. The way that we think about this in JavaScript is we've got to have our primitive types, things like our numbers and strings. We know that they are natively immutable. When you add two numbers together, you're not actually changing a number in memory. You're just creating a new number. You're creating a new space in memory that's holding the new number. Same thing for strings. Whenever you concatenate a string together, two strings together, you're not actually mutating that string in memory. You're creating a new string somewhere else. And this isn't the case in all programming languages. Actually, in C++, strings are mutable data structures. You can mutate them in place, and it's super weird to me coming from JavaScript. So we know that those primitive types for us are going to be immutable in JavaScript. On the other hand, objects, which includes functions and arrays, those are always going to be mutable in JavaScript. You can push and pop, and that's going to mutate that array in memory. You can attach methods, and you can attach properties and mutate objects in place. If number strings and booleans are this, like noble C stack, like standing immutably in the middle of an ocean for all eternity, then objects and arrays are Play-Doh, which you can mess around with however you want. And that's going to be a challenge for us, as we're going to see. So what if, instead of mutating an array in place when we push and pop, what if instead our push and pop operations always behaved like something like array.prototype.map or array.prototype.filter? And instead of mutating that array in place, they gave us a new array instead. Or what if for an object, instead of when we assign a key value pair to that object, what if instead of mutating that object in place, we get a new object in place? That is the idea behind an immutable data structure. And if you're programming in a purely functional language, say like Haskell or Elixir, then data structures like objects and arrays out of the box are going to behave that way. You're not going to be able to actually mutate your array or object in place. You're always going to get something new in return. And that can be pretty advantageous. Let's find out why. Probably the biggest advantage is, of course, predictability. So rather than having a collection of data maintain this internal state that can change and be different in like the various functions that you use throughout your program, you're just always going to get this one value. Essentially, your collection of data becomes, rather than like a piece of internal state, it becomes a value that you can pass around instead. It also makes your programs a lot easier to debug. Like imagine if you've got all of your objects here that you're changing over time, and every time you want to make a change, you're getting a new object. Think about like how easy it would be to implement, say, like an undo operation into an app that you're writing. It would be like trivial, right? Because you could just collect each object representing the state of your application as you change it over time. And if you want to go back, then you just kind of get the last one that you made. They're all physically right there and available for you. That's really cool. And this last bit I touched on just a moment ago is that these collections of values, rather than being these internal state machines, now they are themselves values. Like when you have an array that contains 1, 2, 3, what's important is that that is an array of 1, 2, 3, rather than that array is a specific identifier in memory. So if what you care about is that your array contains the values 1, 2, 3, then with an immutable data structure, that's a lot easier to examine than with a mutable data structure where that array could contain 1, 2, 3, unless maybe you popped it or like maybe you like shifted onto it in like some other function a couple minutes ago. Cool. So here's an example. So here we got this object that contains A with some data inside of it. Very cool. And then this poor object is going to go into LOL function right there, and then something's going to happen. What promises can we make about this object when we console log it after it comes out of LOL function? We can make 0 promises about it. We have no idea what's going to happen because LOL function could be mutating it. It could change the value of A. It could take the value of A away. It could add on a whole bunch of different things. Like, we don't know. And that's And while this is kind of a contrived example, this is sort of a big problem when you're architecting like much larger systems, because you can't know what you're going to get with any object at any point in time. And that makes it really hard to plan later on in your life. So let's talk a little bit about how we could improve LOL function. Probably the biggest thing that we could do is we could make it a pure function. So I've talked a little bit about this. The distinction between a pure function and impure function is that a pure function is going to follow these two rules. So rule number 1, it's always going to return the same value for the same set of inputs. You're never going to get anything different. And the second rule is that this function can't have any side effects. So a side effect we might define as anything that is nothing is going to happen in the function that isn't contingent upon the input. So for example, if we were to do a function that, say, like makes an AJAX call, or it like, I don't know, like draws something on the DOM or something like that, then that function would probably become impure, because instead of just returning a value based on the input, it's doing just like some other stuff that could potentially fail. We could get like a network request and get maybe possibly an error. It's just we're doing something that is like unpredictable and doesn't depend upon the input that we're putting into that function. So we wouldn't be able to call that function a pure function. The previous example with LOL function, that would be an impure function because we have no idea what's going to happen to that object. And an important thing here is that impure functions aren't like evil. You know, like you shouldn't like, and like maybe like pure and impure is like not like the best like terminology, because like it does kind of like have a weird connotation to it, doesn't it? But the thing about impure functions is that they are going to make your state more difficult to manage. So really the trick is to know when to use pure functions and when to use impure functions. Because generally you're going to need impure functions. You know, it's like I just said, like doing an AJAX request is an impure operation, but it's not like we're never going to make network requests in our life. You know, that's actually something that initially annoyed me when I started learning React, which is which adheres to a very functional paradigm. Is that there seemed to be almost this like peevish insistence amongst the community that like AJAX did not exist, and like I just like could not like find out exactly how to do it for a little bit. So that was pretty frustrating. But really the thing is, like, we know we're going to need to use impure functions, and those are going to give us values. So the trick is to know that, like, once we have the results of impure operations, that we process them with pure functions so that we can predict what we're going to, so that we can predict how we're going to change our application afterwards. Yeah, so let's improve LOL function right here. So we've got object again with some data. And what if instead, so LOL function is going to take that object, and because now we're programming in with a functional paradigm, we're going to say that LOL function returns a new object and is going to leave the original object untouched. So now this is pretty sweet, because if we still want the value from the original object, if we still want A equal to some data, then we know it's there. It's not gone. It's going to stay that way forever. And if we want the value of new object, then we know that, okay, LOL function gave it to us, and it's always going to be whatever we program LOL function to do. So in this way, we get a whole lot more, we get a much greater ability to predict what's going on and maintain some sanity over the programs that we're writing. Yes, question?
Is this why there's like a bias against using for each, because there's like no way to use it functionally?
I would say, like, yeah, that's because generally with a for each, you're essentially working off of side effects, right? You know, with a for each doesn't return anything from it. It doesn't return a new array or anything. It just loops over all of the all of the items in an array, and you perform some kind of side effect on them. As opposed to, say, a map or a filter, that's going to return a new array. And it's going to do a calculation for each item in the array and return you a new array that has that calculation applied. So generally, in functional programming land, they're highly preferred. When you start working with React, you're going to see map and filter used all the time, and for each almost never used. Because generally, when you're iterating over a collection of data, essentially, you're usually doing that because you want to apply some kind of calculation to each item in that array. So, like, that's not to say that you'll never use for each again in your life. You probably will, but you will see map and filter much more. Cool. So let's talk about how functional programming pertains to JavaScript. So consider Java. If you've ever seen any Java code, which you may or may not have, but in Java, it was designed from the ground up to adhere very strictly to the object-oriented paradigm. Basically, like literally everything in Java has to be a class or an instance of a class. There's really like no two ways about it. For this reason, and up until like very recently, with some changes in like Java 7 and Java 8, it's been really difficult to program in a very functional style because you can't just go ahead and write a function or a lambda function, as they're sometimes called, the way that you can do in JavaScript. And if JavaScript is your first programming language, that's going to seem like super weird to you to like not be able to do that. But that's sort of the way it is, because for a long time there was this idea that the object-oriented way of doing things was the best way of doing things, because you have like all of your code organized into these objects, these collections of state and behavior. And it isn't until very recently even that we've started to like heed the warnings of internalized state and not being able to just have like pure calculations. So some comeuppance there for Java. I don't want to rip on it, but I do like Java. Clarification. Some other languages, though, on the other hand, like Haskell, Erlang, Elixir, they're purely functional. They were designed, on the other hand, from the ground up to be very functional. So I don't know them very well, but I'm not actually even sure that they have things like like classes. They're like the opposite, like extreme. Like everything is going to be very functional. All of your data structures are immutable. You can't mutate stuff ever. It's always just all the programs you write are going to have this functional structure to them. It's really extreme. In JavaScript land, we can do everything because JavaScript is a language of the web. So you're going to and this is kind of like the story of JavaScript, is that it wants to really make everybody happy, because everybody at some level in their programming career has to use it, because it is the lingua franca of all websites. This is really cool because this means that we can be flexible. We can be really flexible with JavaScript. If we have some program that makes more sense for it to be object-oriented, we can have our classes, we can have constructor functions, we can write in an object-oriented way. But if we have something else that makes more sense to be functional, like programming a UI, in my opinion, then that means you can write in a functional manner. The challenge for us as JavaScript developers is, because JavaScript is so flexible and so like open to like everybody, is that to do either of these, you have to be a little bit extra careful every time that you do them, because there are definitely pitfalls that you could fall into. Particularly for JavaScript, that pitfall is mutability, because objects and arrays out of the box are mutable data structures, and until very recent, there hasn't been like so much you could really do about that. But now that more and more JavaScript engineers have started to write in a functional style, there's a lot more support for writing in a functional manner, and some new features in ES6 as well, which make it a lot easier as well. Cool. So you might have been wondering, like here, while I've been talking about things like immutable data structures, returning a new object instead of mutating an object in memory, you might have been wondering, okay, that sounds all well and good, but that sounds like so rich, like to just go ahead and create new objects whenever you want. How does that affect performance and memory? So probably the biggest way that like I suppose like real like purely functional languages are going to deal with it under the hood is that they're going to implement something called structural sharing, which is that you're going to reuse the existing nodes or references rather than copying and pasting things all the time to make sure that you're being really efficient with the memory that you're using. JavaScript under the hood like may not implement all of this, so a lot of what JavaScript is going to depend upon is its ability to garbage collect. And all functional languages, this is kind of like their big like dirty secret, is that they're going to have some dependency on having an environment that has a garbage collector, because if you are in fact always reserving new spaces in memory and sometimes throwing away old objects, you're going to need some kind of garbage collector in your environment to make sure that things don't get clogged up. But fortunately, JavaScript's garbage collector, to my knowledge, is pretty good. So generally, you're not even going to really need to worry so much about clogging up memory until you get to like really large applications, at which point there are definitely ways that you can optimize. The performance benefits, they're definitely going to depend on what you're trying to do. Generally, a lot of actual functional data structures their performance is often going to be pretty comparable to a mutable data structure. So like on the one hand, say like just mutating a property on an object. It's just like a straight up O of 1 operation. You're just going right ahead and changing it at that address. Like you really can't beat that. But you can get pretty close. You can definitely get to like something more like logarithmic time with a well-built immutable data structure under the hood. And at the end of the day, it could be that having an immutable structure at a lower level can save you a lot more time at a higher level as well. Especially, say, if you're trying to, say like you have a DOM, for example, like your DOM, is just a tree. You can kind of think of it as like this big tree that starts with your HTML tag, and then your body tag, and then all of these other tags that kind of like flow down into that kind of tree structure. For example, you want to tell if you need to update a portion of your DOM, then if you're writing in like a functional style where you simply are going to say it's like, okay, here is an object that represents what my DOM should look like, then it's a lot easier to selectively decide which parts of the DOM you want to manipulate and which you want to leave alone than if you're just kind of mutating it in place, because then you may have to traverse your entire DOM tree to tell what changes need to happen there, which is going to end up in real life being quite a bit more expensive because the DOM is actually a pretty older piece of technology and can be kind of expensive to manipulate, which is kind of unfortunate. But this is kind of where React comes in. Cool. And so this is the part of the lecture where I kind of try to sell you all on React, and it's always been awkward up until just now because we used to teach Angular, and I would give this lecture, and I always feel like the need to be like, but Angular is good too, guys. Don't don't worry. While at the same time, I'm up here, basically, evangelizing for React. But here's kind of, here's kind of how they differ, and kind of the advantages and disadvantages of each. So in Angular, so both Angular and React are going to be are libraries that will allow you to build front-end applications. So right now you're familiar with just straight up manipulating the DOM using things like document get element by ID and things like that, or using jQuery where you say $ and attach click listeners. Angular and React are both libraries for essentially doing all those things in a much more organized, much more sane way, because building extremely large applications with jQuery is absolutely a nightmare, and you don't want to do it ever. But the way that they implement this organization is very different, and it's a very educational difference. So in Angular, there is what we would call two-way data binding. So we have, say, an object that represents the state of our application, what our application should look like, whether, say, a warning should be displayed above our input, or whether a button should be disabled or not. It would be on an object, and that object is going to be a mutable object. So in response to some user interaction, like clicking or filling in a form, we're going to mutate that object, which is going to then, in turn, mutate the view in the DOM. And this is really great for a lot of use cases. It's especially good for if you want to really quickly get off the ground running. You can implement some very complex logic really quickly. The downside of that is that because your state depends upon data mutation, it can cause a lot of problems down the road because your code will just gradually become more and more unpredictable and harder to maintain. React, on the other hand, data only flows in this one direction to the JavaScript that controls your views. So essentially the view that you see in the browser is, we might say, is just going to be a pure function of a state object that you input. It's sort of like you take your state object, insert it into like a coin slot, and out pops your new view. That's how it operates. So any interaction that you make that's going to like change the way that things appear, say like you're going to click something and a button somewhere else is going to become disabled, or a little message is going to appear, that's going to change your state at a high level. It's going to swap out the old object for the new object, and it's going to just run through the function that generates your UI. So that lends itself to immutable data very well and immutable functional ideas. And at the end of the day, it's going to result in you having a much more predictable UI. The only problem is that it can be a lot more work up front because there's just a little bit more like thinking and planning that needs to go into it, and sometimes a little bit more boilerplate as well. So here's like how like Angular does things. So say you have, this might be your HTML template over here on the far left. So we've got a div that has an h1 in it, and then we're going to interpolate some value that we're going to call greeting. Okay. So then we have this object that represents the state of our UI, and that's going to be called in Angular $scope. That's just the special name for it. But really it's just an object that has a set of key value pairs that correspond to what we want to show in our view. So we might say we have greeting, and that's going to be hello world. So that means that what we're actually going to see in our UI is hello world is going to be between the h1 tags right there. So then say like in response to some user interaction like clicking a button or like filling out an input, that is going to mutate that object. So greeting, that we have that same scope object in memory, and we're just going to change greeting to be goodbye world. So we're going to mutate that object, and that is going to then in turn just right away mutate the view as well to be goodbye world. So pretty straightforward. Cool. The way that it behaves in React is a little bit different. So we the corollary the corollary to $scope in Angular is going to be this object just called state. So that is the same thing, $scope in Angular and state in React. You can think of them as the same way. They're describing the state of our application. So the way that we get our view out there is through this function, a pure function called render. And that's going to give us the h1 tags again, and that's going to render out this .state.greeting, just like the greeting from our state object right there. So we see hello world the same way. So then the difference here is that now when we have user interaction, rather than mutating that state object, we're going to go right back up to the top. We're going to swap out the old state object where the greeting was hello world with the new state object where the greeting is goodbye world. And then we're going to run the render function again, just the pure function that's giving out our view. And then that's going to give us goodbye world. So in a sense, our state object is going to be the input to the render function, which is going to output goodbye world, our view. Cool. So any questions on these differences? Yeah. Can you ask my friend, Mike? Yeah.
I guess I don't get the difference between the React and the Angular. Could you just go back to what's mutable and what's mutating exactly?
Yeah, so the thing that is causing the mutation is, say, like user interaction. Like imagine like beneath that h1 tag, I have like an input, and when I type into that, I want whatever I type to show up in like these h1 tags. So in Angular, when I type into that input, that's going to directly mutate my my scope object right here, and that's going to change it to be, let's say I type goodbye world. So now the greeting key is going to have the value of goodbye world. So we've mutated this object. which Angular is going to bind to the view so that the view will also update to say goodbye world. So in React, see, like I'm going to do that same thing. I'm going to update it so that I'm going to write into that input so that it says goodbye world. Only instead what's going to happen is that instead of mutating this original state object, this state object is just going to like go away, and we're going to replace it with a new state object where greeting is going to be goodbye world instead. And this is all like a little bit like conceptual and contrived. You'll see like a bit more once we get into like actually doing React. But it's more like just like to make the difference between a front-end framework that's built upon mutating data versus a front-end framework that's built upon immutability.
So can I be sure that I'm following you? Is that in Angular we have object properties that are tethered to something in our HTML, whereas in React they're tethered to the output of a particular function?
Totally, yeah.
Okay.
Yeah, I think that's a good way of thinking about it. Cool. So just kind of like a quick call out to a library called Immutable. Immutable JS. It's a JavaScript library that will in fact give you immutable collections. It's very popular with users of React and Redux, which you're going to become very soon. And there's also a proposal to add immutable data structures to the JavaScript language natively. No relation to the library, but just pretty cool because that's something that might be coming down the pipeline pretty soon. I think that would be really cool. But the way that you use Immutable JS is it's going to have an interface really similar to the activity that I described earlier, where instead of pushing and popping, mutating an array in memory, it gives you a new array. So here, say like if we want to have an object with immutable, we would say immutable.map, because an object would be a mutable map. And we would give it our regular JavaScript object just to like get it started. And then when we want to say get value, we want to get values off of it, we would say map.get, and we would give it the name of the key, and that would give us the value. And then if we want to change a key value pair, we would say map.set, and set map.set equal to, and we would store the result of map.set in a new variable. Because map.set won't go ahead and change that original map. It will instead give us a new map that has the mutation that we've applied. So when we say map.getA, just like our original map, that's still going to have A equal to 1. But our new map, which we created when we said map.set, is going to have A equal to 100. Same idea with immutable lists, which are going to be the immutable version of arrays. We would create our immutable list, we can get its size, and then if we pop, that's going to give us a new list. So our original list, its size is still going to be 3, but our new list, its size is now going to be 2. We can predict what the case is going to be for either one at any point in time, because they're not going to change. Cool. So Git and immutability. How does all of this come into play now with Git? So with Git, you've all probably started to use it. If you haven't been using it, then just like suffer through. Don't worry, it gets better. But with Git, your data is never destroyed, right? You can always get it back as long as you've committed it. It's never going to go anywhere. You can always go back in time and find out what you had before. So you might be thinking like, would that like get like out of hand? So, because like think about like a really large application, right? So you've got like probably like hundreds of thousands of commits, and for each of these commits, like Git has to keep track of everything you've ever done. You've always got to go back in time. How can it do that efficiently? And the answer is given to us by this thing I mentioned earlier called structural sharing. So let's think about Git. So Git is essentially going to be a graph or a tree. So each commit, say, in Git is going to reference a tree and its parent. And each tree is going to reference the files in your project or other trees. And then each file is going to be identified by a hash of its contents. This might actually be like a little bit easier after an example. Let me do a quick example here. And this will also help like kind of clear up what I mean by structural sharing. Let's say that we've got that we've got a node here, right? So I'm just going to make this this node with a value of 1. So this node right here, we might say that it represents an array with just the value 1 in it, right? So let's say, what if we want to add something onto this array? So let's say we also have this value. Let's say we want to unshift onto it. We want to create a new head. We have this another new node that's going to have a value of 2. So we want to create an array that has a value of 2 and then 1. So what we could do is we could take this node right here, and we could point it at this node 1. And then if we were to traverse this list right here, we would say that this node here represents an array of 2 and then 1, right? Because if we had this node, we could say, okay, we got 2 here, and then we got 1. At the same time, though, this array where we just have the value of 1 is actually totally preserved, right? Because if we had this node doesn't know anything about node 2 right here. It has no way of accessing it. Only node number 2 knows about node number 1. So only from this node can we get this array with 2 and 1. But a 1 right here is not changed. Even though 2 is pointing at it, that's 2's problem. 1 is totally not changed. Cool. Is everybody following this so far and wants to ask Mike a question?
So going back to your discussion of garbage collection earlier in functional languages, ideally, if you created 2, so 2 is now an array of 2 and 1. Would 1 get sort of sucked up by the garbage collector, assuming it wasn't being referenced? Is that sort of the ideal?
Yeah, so if 1 wasn't being referenced, then it would get garbage collected, but it is being referenced in this example still because 2 has a reference to 1. So if I was a garbage collector, I would be looking at all the nodes here and saying like, okay, this 2 is still referencing 1, so let's not garbage collect it just yet.
So it sounds like, because that second node isn't actually storing 2 and 1, it's just representing that because it's connected back to 1. So what you're saying is that each new commit effectively is a new node, but it only stores the changes, not the whole new structure.
Yeah, totally. So yeah, and so that is definitely the idea. And let's talk a little bit more about like this idea of structural sharing too. Like let's do something that's a lot harder, right? So here we did this unshift operation, and that was pretty easy, right? What if we want to create a list that looks like this now? So what if we want a 3 here? Yeah, so what if we do let's see if I can. So what if we were to do this? What's the problem with what we're doing here? Yes, maybe. Actually, I realize that having you answer questions, having to come up to mic is cumbersome. But yeah, so I'm going to infer that you had the correct answer, and that is that to do this, we would effectively be mutating our previous 2 nodes. This 2 right here, this node would no longer represent an array of 2 and 1. It would now represent an array of 2 and 1 and 3. And so on, like with 1, we would no longer have any record of a node that was ever just an array of 1 or an array of 2 and 1. It's gone forever, lost completely to the annals of history, and there's no way we can ever get that back. So here's what we would do instead. Now in this case, because we have to, because we're trying to essentially do a push instead of an unshift, what we need to do now is we need to create new nodes. So now we want to make sure that these nodes continue to exist. So if we want to have an array with 2 and 1 and 3, then we're going to need to create a new 2. Let's call this like 2 prime, which is going to then point at this new 1, which we might call 1 prime, which is then going to point at our new node 3. So we did have to create some. So we did have to create some new objects. So this was definitely a lot more of an expensive operation using a functional data structure than the unshift operation, which is going to make. So when we see how Git is structured, we're going to see why it makes sense that it does things the way that it does. But to do like one more example to show how we can be conservative of memory here, let's say that let's think about instead of just doing like a regular push or a pop, let's insert something. Let's say that we want to have, let's see. Let me think of how I want to do this here. Let's say that I've got this this other node. I'm just going to like draw it up here, and this is going to be 4. Let's say that I want to end up with an array where I have like 1, 4, and then 3. So what do I need to do here? So I want this array in the end. So I need to think about like what nodes. So what am I going to need to do? I have this node 1 right here and this other 1 prime right here. But if I point either of them at this 4 right here, things are going to get messed up because I'm going to lose what I had before. I'm going to be mutating. So I'm going to need to create a new. This is going to get a little bit squished. Sorry. Like a new 1 like double prime. And that's going to point at that 4. Cool. So now I want 3. So now now here's the interesting question: is do I need a 3 prime? Who here thinks I need a 3 prime? Raise of hands. Nobody is. Okay, one person has raised their hands. You're wrong. Sorry. I'm sorry. Okay. I'm sure you do that just to make me happy. No, because remember that because this is just a singly linked list, we can share the existing structure and just point this 4 at this 3. We don't need to create a new node because this 3 has no idea that this 4 even exists. Only the 4 knows that the 3 exists, so we don't need to create a new 3 right here. So this is essentially the way that Git, which is structured in this exact same way, it's just a singly linked list, is going to be able to like just keep track of the things that change and not create a whole bunch of new stuff every time you like do something trivial like just like take away a space or something like that. Cool. So I think I had one more point I wanted to make about this here. But I think that oh yes. So a really important property of these nodes right here is that this is all a singly linked list, right? What if this was a doubly linked list? What if like each node also knew about the node before it? Would we be able to do any of this cool stuff that we've just done? The answer is no. And this is if each node also knew about its parent, then basically we wouldn't be able to do anything but mutate these nodes. We would not be able to like have like any good sense of history, and we would lose track of anything that we had before. And this is really cool because I remember way back when I was first learning this stuff, I learned about the difference between singly linked lists and doubly linked lists. And I was like, oh, okay, doubly linked lists are just better than singly linked lists because they can do more stuff, right? And like it's hilarious because that's totally wrong. Singly linked lists, actually by nature of the fact that they have fewer features than a doubly linked list, are actually a lot more powerful. You can do quite a lot more with them than you can do with a doubly linked list. And I think that's something that is also just like a really good lesson for the functional programming in general, is that less is more. Like when you take features out of something, you're making it simpler, which means you're also making it easier to understand, easier to use, and easier to maintain. So if there's like one takeaway actually from this entire class, this is probably it, is that less is more. It's sort of like a philosophy that I would hope like all of you would have as developers, like not just in the way that you structure your code, but also in the way that you structure your applications. Don't be maximalist, because the less stuff you have, the less that you have to maintain eventually. If you always try to do more with less, like there's like a life lesson in there too. I'm sure. But yeah, so like returning to Git now. Git has like essentially that same structure. So we have these commits now that reference trees, which essentially is just going to be just like another singly linked list representing all the files in your project and its parent. And each commit is just going to singly link, like from like parent to like child. And in that way, you have this. You can keep track of the entire history of your project. So here's a better example because it's visual rather than me blathering. So like let's say here we've got this one commit, which this right here is say like the future, and this is the past. So this is like our latest commit, or a commit we might make in the future. It knows about its parent right here that we're saying making in the present. So we're going to make this commit. And it's going to singly point to this tree, which might be like my project, which is going to then point to say like my project /JS, which is then going to be like my project /CSS, which is then going to point to all of these what we would call blob objects, which stands for binary large object, because the actual files that you create in your project, when Git gets to them, it compresses them into binary data so that they're as small as possible, because there are going to be a lot of these, like the longer and longer you use Git. So it just compresses them to make them very small. So now you can see, like, if these arrows were to point like both ways instead, then we wouldn't really be able to keep track of, like, essentially we would lose our sense of history. We wouldn't be able to like go back to what we had before anymore, because we would always be mutating the relationships that all these objects here have to each other. Cool. So another cool way that Git tells whether like you've even made a change or not is through what's called content addressability. So Git's objects, whether they're commits or trees or blobs, are always going to be content addressable. And the way that it does that is that it uses a hash of the contents. So who here remembers like what a hashing function does? Yeah. So like a hash function is like this just very special algorithm that is itself a pure function. It's a pure algorithm. You can put some string input into it, and what you're going to get out of it is going to be, say, for like is going to say maybe like a 40 character hexadecimal that's going to be unique for that input that you put in. So for example, if you have a hashing algorithm and you put in the text hello world into that hashing algorithm, then you're going to get a 40 character hexadecimal string that is going to be unique to hello world. If you put the text of War and Peace into the same hashing algorithm, like thousands of pages long, and what you're going to get out of it is a 40 character hexadecimal string that is unique to the text of War and Peace. If you go into War and Peace and you say like you change a period to be a comma, maybe somewhere in War and Peace, and you put that into the hashing algorithm, you're going to get a 40 character hexadecimal string that is unique to War and Peace with that one character changed. Even though you've only changed one character, you're going to get something completely different and unique from that hashing function. And that's really special, because now if you think about the like the files that you maintain, like your projects, like it would be really cool, because now you can immediately tell in any project, any file, if you just parse it into a string and put it into a hashing algorithm, you can tell right away whether just through evaluating the equivalency of their hashes, whether something has changed or not. And then using that content addressability, Git can tell whether it needs to create like a new blob, a new node, or whether it can just reuse an existing node that it has already created somewhere for you. So that's pretty cool. That's sort of like the secret behind how Git is able to tell whether it needs to create new things or not. Is there a question to go to Mike, or?
Do they use things like do these hashing algorithms actually go in and look at the text, or are they using things like file size, date modified, stuff like that? Like if you change a comma, is the hashing algorithm just kind of recognizing that the file got changed, taking like the timestamp, you know?
Yeah, well, I mean, like, because well, consider if it was just going to be like the timestamp. What if the change that you make isn't actually a change? You know, like maybe like you like save the file, but you didn't actually change anything in it. You would still want to be able to tell whether I need to create a new node or whether I can reuse the existing one. So what's going to do is it's just going to take your text and it's just going to hash it into this 40-character hexadecimal, and then using that, it can compare it to the 40-character hexadecimal that it had before, and see like, okay, did this change? No, it didn't change, so I don't need to create a new data structure. I don't need to create a new node.
So they're taking every single character and passing it through the function.
Yeah, totally. It's pretty quick, right? You've all used Git. Totally works. You're gonna do it yourselves in a little bit. Cool. So last fun fact: the algorithm that it actually uses is called SHA-1, Secure Hashing Algorithm Number 1. It's the primary one that's used by Git, and we're going to use it today as exposed through the crypto library, just for fun, really, more than anything. Fun fact is that it's not actually going to be, SHA-1 is not actually going to be used for real security purposes pretty soon because it has like totally been cracked, so like you'll probably already start seeing like in browsers if a website is using SHA-1 to encrypt, say like encrypt like the messages that you send through it, then you're going to see like a warning in your browser saying it's like, hey, this website is using SHA-1, you need to get your life, so like, but it's still perfectly fine to use for content addressability because as a hashing algorithm, it still does its job of giving us a unique output for a unique input. Cool. Let's have any questions come up to the mic real quick.
I had a question about the last slide.
Yeah.
When it says expose the node via the crypto module, does that mean if you have the crypto module a node, you could, I guess, solve the algorithm? Is that what that means?
Well, I mean, the like SHA-1 algorithm is like you could look it up yourself. It's not secret or anything. The crypto module just gives it to you so that you can use it. To crack it, you would need to reverse engineer an output back into its input, which you can't do with crypto because it doesn't give you a method for doing that, like to my knowledge, at least yet. So that's going to be like a little bit harder. Like maybe like do that as like extra credit. But no, the SHA-1 algorithm itself is. I forget actually whether in like a later CS Saturday with Omri you might like make it yourself. It's like not terribly difficult. But like the thing with these kinds of algorithms and with cryptography in general is that you want a function that is going to be very easy to encrypt something, but then very difficult to unencrypt it. And that's like kind of the idea behind what you want with a SHA-1 hash. And that's like the idea behind public key cryptography, which we're not going to talk about, which is super interesting and I love. So like stay tuned for like more fun with that in your lives. But yeah, so cool. Let's workshop. Any final questions though?
I was just a little bit confused by your diagram when you were creating, 1 prime, 2 prime,
Oh yeah.
et cetera. And I wasn't exactly sure when you need to create like the new set of fake parent objects.
Yeah. So let's. I don't know if I don't know if I can copy and paste this, but we need to create a new object if creating that object if like creating a new linkage is going to mutate something that we had before. So think about like right here, going back to when we thought about the possibility of linking 1 to 3. Remember before it was I just tried to cover it up like on my screen. Sorry. Okay. So when we thought about linking 1 to 3, but remember if we did that, then this node number 1, instead of just being a single node that has no reference to anything, that would no longer like exist ever at all because it would only be now be a node that points to 3. Like if you were to think of this as like, say like a JavaScript object, then it might like look something like this, where you have value, oh man, that's brutal. You know, like equal to 1, and then say like next. Nobody can tell what I'm writing right here. We'll say, like, pretend that that's next. And next is going to be equal to null. So if we wanted that to point at 3, we would need to mutate that next property to point to 3 instead. And that's not what we want to do. We don't want to mutate our this object ever, because then we're going to lose the old one. So instead what we need to do is we need to make this new one 1 prime and point it at 3 instead if we want that value. Yeah, and this is also exactly what you're about to be doing in the workshop too. So get ready for that. But yeah, so like workshop, yeah, you're going to be creating an immutable linked list just like this. So I hope you paid attention to that part. Anyway, so the spec is going to be in spec/list.spec.js, and you're going to work out of list.js. So just like here real quick, I can pull it up myself just to make sure, because I have had like, a bunch of times where people have started working on the wrong thing, but none of you will. You will all be correct. So you'll be working out of list.js right here. It's going to look something like that, and the spec is going to be right here, list.spec.js. We'll say functional lists. fvs.spec and all these other fvs files, those are for the next part, so don't look at them just yet. So you don't need to actually like install Immutable or anything like that I talked about. You just need to npm install. For solving these, I also very highly recommend recursion, because a fun fact about recursion and iteration, that is using things like for each or for loops, is that any problem that can be solved using iteration can also be solved using recursion, and vice versa. And some problems, their approach to solving them recursively or iteratively may be more or less difficult depending on which approach you choose. And a lot of the problems that we're looking at today are problems that are going to be much easier to solve recursively than they are iteratively. So word of warning and advice. Cool, but if you have any other questions that you don't want anybody to hear, then feel free to just come up to me. The help desk is on. We have some friendly fellows here somewhere to help you. Don't know where he is. There's Elliot anyway. But yeah, so just go ahead and write tickets to the help desk when you get stuck. But otherwise, this is the address for the repo where you can get started. Just git clone it and get going.
Okay.
Okay, I've got the mic on. Is that coming through? Cool. Oh.
So do not touch the buttons on this mic when you come up there. It's just always live. I turn the volume up and down when you walk up to it.
Oh. Oh, you want to just give me the go-ahead when to get started? Cool. Testing, testing. 1, 2, 3. Patrick the dog is here with me. He's right up here, and he's here to say that he's a stuffed dog in every way. What? You can't hear Patrick? Okay, one sec. He's got a mic right here. Let's get him set up. Can you hear him now? You're really bad at playing. Okay, you're really bad at playing make believe, Tessa. We're pretending he's a real person. I know. Cool. So are all animate people coming through on the mic? Wait, Elliot, we good?
You're good.
Oh, okay, cool. I'm gonna get started then. Is that okay? Is that okay? Yes, no, maybe so. Elliot, can you hear me? Oh, cool. Okay, I'm gonna go ahead and get started then. Sweet. All right. So, how far did everybody get? Oh, I hear nervous laughter. All right. More nervous laughter. Okay. Yeah, probably not super far, because this is actually a pretty hard set of specs. Actually, these two sets of specs, in my opinion, are probably like some of the hardest that we do. So surprise, they're pretty difficult. This one is actually based on like a Q3 problem in Code Wars. So congratulations, you get like a free one after this. But I highly recommend like continuing to work on it. We're probably not going to get through like all the different ones because I want to take my time and kind of go through a lot of this stuff. And I also want to introduce you to a lot of really cool ES6 syntax if you're not familiar with it already. So that's going to take up some of my time as well. But the thing with this, like this whole like list node class, is that once we get the basic idea to how it works, kind of like every single test spec just falls down like a bunch of dominoes. There's like this one it's kind of like clickbait on the internet. There's this one simple trick, and then they just kind of like all really work. It's very elegant and very simple. I really like it a lot. So the first thing I'm going to do right off the bat is, well, first I just want to introduce this syntax down here, destructured assignment. Essentially, so the comments explained it quite a bit, but this is essentially the same thing as if we were saying const get SHA-1 equals require util dot get SHA-1. Same thing right here. It's just that by wrapping it in curly braces on the left-hand side of the assignment, we're essentially it's essentially a shorthand for this, so that we can compact this statement quite a bit. You can see there's a little bit of a horizontal space that's saved there. Is there a question that you want to direct to the microphone?
Sorry, so we were having trouble with that. Does Mocha allow ES6 stuff like that? Because it kept erroring out.
Yeah,
on those
so
brackets.
so if your node version is below node 6, then it's going to error out. In which case, you should have written a help ticket, but because then I would have told you this, and it would have been very, very quick to fix. But two, if you need to update your node version, which I highly recommend you do, I really recommend just npm install -gn, which is a really great library for managing your node binaries. So once you have this, you can just type in n like 6.9.1 to get the latest stable version of node, and then you can just type, my bad. And then you can just type n to change your node version, just like this. So I can go ahead and put myself on 6.9.1, and there we go, beautiful. And then all that stuff will work.
What was that npm install?
And that was, where is it? Oh, I didn't enter it, so it's npm install -g for global n, just the letter n. Tessa has a question that she wants to come up and ask the microphone. Or not.
What if you already have npm installed? Should you uninstall that first?
NVM is terrible and I don't like it, so I recommend uninstalling it and using N instead. Because what NVM does is essentially it changes your path. Like this thing right here that essentially tells your terminal where to find things when you type stuff into them, and it kind of and that really like is screwy, I think, and leads to like some problems down the road, and will actually change your node binary. So it just feels a lot easier to me. But you can also do the same thing with NVM. I just won't show you how to do it because I don't like it. Cool. Yeah, so same thing down here with this module.exports. Essentially by putting the list node that we have here on our scope just into the curly braces, that is essentially extracting it into the object literal right here that we're setting as our module.exports, because what we have here, and this is a fairly common thing that we do a lot in JavaScript, we have like this object that we want to set as a key value pair, and the key has the same identifier that we want to have the key be the same identifier that we already have on scope. And it's really redundant to have to write both of them. It really stinks. So so with this new syntax right here, we get to be a lot more concise. Very beautiful. I love this. Another question for the microphone. Yes.
Just wondering why you can just do it without the brackets, just module exports equals.
Yeah, because, and we could, but in a previous iteration of this workshop, we module exported more things than one. So we're not, sorry, sometimes it's incidental stuff like that. But it's also a good excuse to introduce this. And like say, like what if we also wanted to like export other stuff too? You know, it's like we're already set up for that. So I think it's fine to do this this way. Cool. Cool. So the other thing, but not the last thing I'm going to do, is I'm going to use a class rather than using a constructor function, because essentially, like we got to get the idea behind constructor functions at this point. So you know they're just this function right here, and then we go ahead and we attach methods onto the prototype equals function. You know, like this whole song and dance right here. This is like all pretty familiar to us, but I'm going to use a class instead, which is going to be a little bit different. So a class body is going to be a lot more concise if we're writing something like this, because I can just use the class keyword to create the list node, and this is essentially going to automatically, like under the hood, if you look at a class, it is just a function. It's the exact same thing as a constructor function. So don't think that's anything like super special. But the way to actually get the functionality of a constructor function when you use the new keyword is within this class body here, you need to, always like mess up typing that, you need to write a method called constructor. And you can just type it in just like that, just into the class body, which is really a cool thing about class bodies. You can just type any methods that go on the prototype just right into the class body. It's really cool. So I'm going to do that. So essentially, this constructor function right here, this function that gets executed when I use the new keyword, I am writing that right here. So when I say new list node, this is the function that gets executed. And all the methods that go on the prototype are just going to go right after it, where I say some method and all that jazz right there. But it's a whole lot cleaner than just using the constructor function and attaching stuff to the prototype. I like it a lot. There's some controversy surrounding it that we won't go into, but that's like from like people who I think are being a little bit like overly zealous about it. So I would say don't worry about it. The class syntax is cool. So let's go ahead. Let's actually like write our stuff, right? Okay, so let's go ahead. Let's get started. So we know that our constructor is going to take a value, which is just going to be the value of the node, and next, which is going to be the next node in the list. So let's go ahead. Let's get it started. So we know we want to set this.value equal to value. This.next, we know we want it to either, there we go. We know we want it to be a, oh, it doesn't say right here. It says in the spec, we want it to be null if no next is passed in. So we just need to make sure that, that if next is falsy, sorry, or it's undefined, we set it to null specifically. So, so everybody's probably familiar with this pattern right here where we say next or null, right? So basically what we're saying here is that if next is something that is falsy, we're going to evaluate the right-hand side of this or statement right here and set it to null. So this is like a very common way of, in a sense, assigning default values to parameters. But cool news, with ES6, you can actually assign default parameters very directly. Let's do that. So instead of doing this right here, the equivalent would be in the function definition right here. I can just go ahead and say next equals null. And what this will do is that if next is undefined, if we don't pass in anything for next, then it's going to automatically set it to this initial value of null. So this is very cool, and it does a really good job of replacing this cruft right here. There's another really good advantage of doing it this way is now you don't even need to read my function body to know that this is the function signature. You can go right ahead and look at it, and you don't need to care about the implementation details of the function to know that next is either going to be the value that you pass in or it's going to be null by default. That's pretty cool. That's really advantageous. Cool. So now we got that going on right there. Our function body is now even shorter because of it. The last thing we want to do is we want to set an ID on it. So that's going to be the result of passing the value into get SHA-1. Cool. And that, oh dear. And get SHA-1 right there, if we go and check out just Util JS, the way that we're getting it here is off of the crypto module, which is a built-in node module, similar to, say, like HTTP or Path or FS. It's built into Node. So we simply have a simple method right here, get SHA-1, which is going to return the result of saying crypto.createHash with SHA-1, that's the kind of hash that we want, update with the data, and also digest with hexadecimal format. So the output that we get here is going to be hexadecimal. Another fun thing that you're going to see right here is the way that I have written this method into this object literal, or module.exports. It looks really similar to the way that we did things with the class body, right? That's because you can do that with object literals now too. You can go ahead and say you have some object. And before, if you wanted to write a function into it, just like that, you would have to use the function keyword just like that, but you don't even need to do that anymore now. You can go right ahead and just, go right ahead and just kind of write it in there very similar to the way that you would with a class. The only difference here is that because this is an object literal, not a class, is that if I want more stuff, I need to use a comma, but I don't need to do that with classes. So that's the only difference there. Cool. So I just dropped like a huge ES6 bomb on everybody. So is anybody upset with any of these features or uncomfortable? Yeah, sorry. This is like stuff I really like, and as like ES6 becomes like less and less, or like more and more old news, it's just going to be more and more expected that JavaScript developers just kind of know it out of the box. So I just kind of want to, I really want you guys to get the hang of this as much as possible. But cool. So but that's most of the new stuff. I think there's one more new thing that we're gonna get to. But yeah. So let's make sure that we just got our constructor working properly. I got the test specs running right over here. Let's see how we're doing. Great. Okay. We have our constructor function, and everything is working. So now we need to write a toString method. And what that's gonna do is it's going to output a string with square brackets with each ID separated by a space. So let's go ahead. Let's do that. So I'm going to just go right ahead and write toString. So like I said before, any problem that can be solved iteratively can also be solved recursively, and vice versa. And this is a really interesting one. A lot of the other problems on the spec are a lot better to solve recursively. toString is actually a little bit easier to think about iteratively, but there is a recursive solution as well. Let's solve it iteratively and then recursively, because that's fun. So let's go ahead. Sorry. So let's go ahead and solve this iteratively. So what I'm going to do is I'm going to go ahead and say let cur equal this, okay? Because essentially what we're going to be doing here is we're going to want a while loop, and we're going to want to loop through our list and accumulate the string that we want, and then at the end format it and return it. So let's go ahead and let's say while cur is a truthy value, we're going to do something. And what I'm also going to do is I'm going to set aside an array of IDs, let's say. So just like all the IDs that we're going to be accumulating here. Okay, so while cur is a truthy value, here's kind of what we want to do is we want to say some like IDs. Let's go ahead and let's like push in cur.id. And then after that, we're going to want to reset cur to be the next thing, right? So let's say cur for like the current node that we're on equals this.next. Cool. So let me make sure that I've actually done this right. Cur IDs.push cur.id this.next. Yeah, I think that might be okay. I think I'm forgetting something, but we'll keep going. So now once we have that array of IDs, we know that we want to return it formatted such that it's going to have brackets on either side and it's going to be space delimited. So so we can do that with just like a little bit of array manipulation here. So I'm just going to return, let's say, just a bracket plus, and I'm going to say IDs.join with a space right here, and that's going to join all the IDs in the array as one string with a space separating each ID, and then end it with the other bracket right there. So let's see. So let me see if this is actually going to work. And a good way to like see if it works in my head is just to run it through like a very simple test case. So let's like do like just like a simple test case where we only have one node. Let's do like one node. So if we have one node and we're saying toString on it, then cur is going to be this, IDs is going to be an array, and while cur is truthy, so we're entering this this while loop right here, we're going to push the ID into our ID array, and we're going to reassign cur to be this.next, which is going to be null. So then when we go around this while loop again, that check is going to fail. We're going to not enter the while loop. And instead, we're going to return this, which I think is correct. Cool. So let's do this again with two nodes now. So we got two nodes. Cur equals this, IDs, empty array. While cur, that is true, IDs.push, cur.id, that looks okay. Cur is going to be equal to this.next, so now that this is another node. That's truthy, so we do this again. We push the node's ID in there, and then we set cur equal to this.next. Excuse me. And so now, which is going to be null now. So then when we get to cur again, that's going to be false, and then we do this. Okay, so I think that's okay. Let's see if we're actually passing then. If we're, oh, no, cool. I'm totally blowing the stack, I think. Stack trait.
Does it need to be cur equals cur.next?
Yeah, totally. That is this mistake that I always make. Cur.next. Beautiful. Okay. Let's see if abort trap. Okay, great. Let's try one more time. 4 passing now. Great. There we go. Cool. I always make that mistake, like every time I do this live. Cool. So this is a really nice little iterative solution right here. But we can do this recursively as well in fewer lines of code too. So let's do that. And to do it recursively, we're going to need to do a little bit of a trick, a little bit of cheating, in my opinion. Well, not really cheating, but we're going to need some way to keep track of this array right here that we're accumulating, because this is, I think, this is a good approach. I think we're getting this array of IDs and then we're joining it all down here. I think that's pretty good. But if we're doing this recursively, then we're constantly entering the scope of a new function, and we can't really keep this like array around anywhere. And if we don't want to do something like really gross, like put it like somewhere outside in our module somewhere, that would really suck, I think. So here's what we're going to do: is we're going to just we're going to take this array and we're going to pass it along to each recursive call as we go. And I would call this I'm going to call this array memo. I'm just going to call it a memo, just like that. So because essentially it's something that we're passing down for further recursive calls of our function to like keep track of. And I'm going to initialize it as an array using this awesome syntax that we just learned. So the first time we invoke toString, memo is going to be an empty array. Cool. So let's get rid of all this for the moment. Cool. So this is how I'm getting started. Because I know I'm going to want to have, every single time I call toString, I'm going to want to essentially say memo.push this.id, right? I totally am. But I also kind of don't want to do this because not for any functional reason, we could continue to do this and it would work just fine. It's just that now that we're doing things in a functional way, why don't we do this like immutably, right? Why don't we like not do a push and mutate? What's like another operation that we could do? Somebody can shout it out. Because I'll. Concat. Yes, concat. Concat is awesome. Is an awesome alternative to pushing if you want to maintain immutability. So I could instead say memo equals memo.concat this.id instead. And I think this is a slightly better alternative for the way that we're doing it. And it gets even better. I'm sorry, I forgot 2 more new things I'm going to show you. Okay, so this is all well and good, but there's also like a nice shorthand, again, that we can use using a brand new operator in ES6. At this point, you must be like getting really sick of me like dropping new things. But that's called the spread operator. So when I create a new array just like this, and I use the spread operator on an existing array, essentially what that's going to do is that flattens that existing array out into this new array, and then I can continue to go ahead and add new stuff. So I can go ahead and say memo equals memo with this.id. And this is the same thing as saying memo.concat this.id. And I like this. Not everybody likes this. I like this. So I'm going to go ahead and keep it for now. This might look really bizarre, and it's weird too because this is a brand new operator, just like the plus operator or the minus operator. But it is very cool, and you're going to see this quite a lot when you get into React, because this is a very common operator that's used to maintain immutability with your arrays when you're doing things like updating something in your in React. It's a really useful thing to learn. Let's go ahead and just keep using it for now. I'm gonna just comment out that line. Oh, nope, I didn't want to do that. Let's just get rid of that right there. Cool. So we got this memo. So now we have, so now let's think about this recursively. When you're doing recursive problem solving, you really have 2 things to keep track of: your base case and every other case. So let's think, what is the base case for toString? Yeah, let's run up to the mic.
If this .next is like a falsy value?
Yeah, totally. If this .next is a falsy value, because imagine we just have one node. Again, remember, that's a really simple example. This .next is going to be null. So let's go ahead and let's plan for our base case first. So that would be if not this .next. Then what we can do here is we've got our memo, and let's just assume that our memo is just going to be that array with that one ID in it. We can go right ahead and we can do that thing that we did before where we have this plus memo.join with spaces. Cool. So we can go right ahead and we can do that. So now all we need to do otherwise is just think about what is every other case. Now what do we do when this.next is not null? This is our recursive case. And we already know at least one thing about this case, right? Is that we're going to invoke toString somewhere. We're going to invoke it recursively. And here's what I think we can do, is because we've already added the ID that we have currently to memo, we can go ahead and we can start to invoke toString on the next item in the list. This.next, we can return this.next toString and pass in that memo that we put together. Because here's how this is going to work. Now let's imagine once again that we're running this function with just one node with some value and this.next equal to null. So what we're going to do is we're going to enter the function. Memo is going to be, we're just going to invoke it without passing anything into it. So it's going to be this empty array. Then we're going to concatenate this.id onto the empty array. So it's just going to be an array with that one ID in it. And then if not this.next, this is true. So we're going to just return, the brackety version of it. And I think that's totally going to work. So now let's imagine two nodes. Okay, so we already know what happens up to here the first time, but now this is going to be false. So instead, we're going to return the result of saying this.next.toString with the memo that we've already done. And so now this is going to be the same as when we invoked it with just the one node. But the only difference being that instead of being an empty array as the memo starting out, it's the array with our one ID already loaded into it. So we're just going to concatenate the next ID in there. Not this.x is going to be true, and then we're going to return the stringified version of it, which is going to come out to this space right here out of this function call, which is then going to get returned out of our initial function call. And that should totally work. This should still be passing. It totally is. Yeah, cool. Questions up to the mic. Feel free to get in line. That's okay.
Why do you use a tracker variable? Because you can do this without passing something through, right? That's what we were trying to do. Our line 14 and 16 were kind of combined into one. We just returned the concatenation of ID and toString on next.
Oh yeah, you probably could do that as well.
We had trouble with whether it was an array or a string when we finally returned it.
Oh.
So that was our issue. I don't know if there's a way to do it without that. I just feel like I never want to use a tracker variable in recursion. I don't know if it's a good idea or not.
Oh, it's fine.
I shouldn't have that.
Yeah, it's fine. I mean, it's something that you actually do quite a lot to solve certain problems. You'll hear about this thing called dynamic programming, which is what I was hoping to get at with this, where essentially you're passing along a tracker that you're using to cache the values that are returned from certain recursive calls, which can eventually cut down on the number of function calls that you actually have to make. It can reduce. You can use this to solve for the Fibonacci for very large numbers, because you're caching the values of Fibonacci at certain for certain inputs, so that it can turn an entire side of a recursion tree into just a simple O of 1 operation. So it's totally fine to use tracker variables like this. Cool. Let's do the next one. Let's do length, because we're almost out of time too. But that's okay, because after I do one more of these, you're gonna totally get how this works, which is fine. So length, I think so. I don't know. If you don't, that's totally okay. But I don't know. So length, let's think about it recursively. So what is the base case?
Same thing.
Yeah, totally the same thing. These are all gonna have pretty much the same base case, if not this dot next. So if not this dot next, imagine again if we just have one node, what's that going to be? What is our length going to be? The answer, because the mic makes things difficult. It makes it difficult to do my normal song and dance, but it's going to be 1. So we can just return 1, and that's going to solve for when we just have one node. But what if we don't? So if we don't have one node, then if we think about it, we know that if we have 2 nodes, so if we simplify it to just 2 nodes, then we're going to get 1 from a recursive call to length. If we say this dot next dot length, that's going to be equal to 1. So what if instead we return 1 plus this dot next dot length? So for 2 nodes, then we're going to return 1 plus this dot next dot length, which is then going to be 1 if we just have a node that has a length of 2. And that's going to remain true no matter how many nodes we have. Yeah, see, now this is really pretty. Cool, so yeah, cool. So that passes as well.
Can you do append?
Append? Yeah, I'll do append in a moment. Let's do a shift node really quick, just because it's so easy. So shift node. Remember when I was drawing those nodes on the board, and we had our node number 1, and then I just shifted node number 2 right onto node number 1. That was really easy. We didn't have to create any new stuff. That's what this is right here. This is a very easy operation. We're getting this value that we're getting passed in, and we know that value is going to be a new list node. And remember that new list node that we're creating is going to point at our current list, which is going to be the node that we're invoking shift node on. So we can go right ahead and just throw this in as the next of the new list node that we're returning, just like that. We can return new list node with that value, and then it's just going to point directly at this, the node that we're currently on. So that should totally pass. Yeah, sweet. Cool. So now append. And this is where I'll stop because not only because we're almost out of time, but also because after this, like dominoes, you know, it's totally gonna fall. Cool. So now this is now append, which takes another list. Yeah, it takes another list, which I'll call ln for list node. It takes that as its argument. So this is the harder case from the example that we did when I was drawing on the virtual whiteboard earlier, because we had 2 pointing at 1, and then I introduced 3, and when I introduced 3, we needed to create 2 prime and 1 prime because we didn't want to destroy the previous list that we had before. Cool. So append. Again, let's solve this recursively and think about what our base case is. So our base case at this point is, again, just like let's think about if we have one node. So if not this .next, we just have one node right here, and we're appending this new list. And we don't want to destroy or mutate the node that we have right now. So instead of mutating it, we're going to return a new list node with this .value, and as it's this .next, this new list node is going to have ln right there instead of null. So this new list node that we're returning has the new list that we're passing in appended to it without mutating the one that we've invoked append on. Cool. So now otherwise, we go ahead and we need to think about like, okay, now we have 2 nodes. So let's think about this here. So now this was the actual case that we drew on the whiteboard where we have 2 prime and 1 prime. And we know that for each node, we're going to create a new list node. So, sorry. So we know we're going to need to create a new list node that's going to still have the same value. And then its next. This is actually, so this is like a bit like the clever part. Like its next, we're going to need to also recursively invoke append. So we might go right ahead and say that the next value of the new list node we're making is just this .next .append ln. And that's going to, now let's imagine for the case with 2 nodes. So we have 2 nodes now, so we're invoking this on, say, like node number 2 right now, and from our original example where like it's 2 and then 1. So this .next is not falsy, so this fails. So we're going to return a new list node, the same value, and we're going to set as the next of that new list node this .next.append. So we're taking that list node with the value of 1, and we're invoking append on it. So it's like pause that right there. So now we're in append on the node with the value 1. If not this .next, that's totally true. So we're going to return a new list node with the same value and the list appended to it. So now that's going to go right back to where we left off with node number 2. So unpause that. That's going to be the new list node with the appended value, and then that new list node gets returned out of there. So now we have 2 prime and 1 prime that is pointing at the new list that we passed in to append, and that should totally pass. Yeah, it totally does. Yeah, question up to the mic.
Since you're making new nodes, don't you want them to have slightly different IDs and therefore a different value? Like maybe put a prime at the end since the ID relies on the. No, it doesn't actually matter for like these specs. Not for the specs, but
are like for what we're doing here. Mostly this is just to introduce you to get SHA-1 because you're going to be using it shortly. If we wanted to have it be like a different ID, then we would be calculating it a little bit differently. Like say, like for example, what I would do instead is I would make it like a SHA-1 of 2 string, which is probably like how like I'm like supposed to do it. But I think like I took that part out because I was worried it would be too hard, like way back when. So that's like the kind of like the story behind that. But like you are right, that is very observant that like these IDs like should be different, right? But they will be the same with the way that it is. Yeah, not a perfect thing right there. But cool. So any other questions on this approach? Well, anybody still like not grokking the sort of like this like recursive method that we've been going over? Because like yeah, like it's like really elegant and really clean. I like it a lot, and just kind of like following this same method for a lot of your problem solving is going to be really useful. Just say like, okay, what's the base case, and then what is every other case where I know I'm probably going to need to invoke that method recursively. You're going to solve a lot of problems that way, and you're going to wind up with code that's really nice and clean like this. So we won't do any other of these. I recommend going and like doing them yourself at some point. But pretty much like big hint, the rest of them are going to look a lot like this. You know, there's really it almost like to the T. I kind of wonder whether like a control F could like possibly like solve like a lot of the other ones for just kind of like using the same pattern. So big hint going into the rest of them. But you know, try to forget it a little bit so that you can learn it again. It'll probably take a couple times to sink in anyway. So we're a little bit over time, but let's go ahead and let's take a like a 10-minute break, and then we'll come back for the lecture on Git. Testing, testing. Okay, cool. Oh, cool. There we go. Sweet. Okay. Let's talk about Git. Cool. So, like, what is Git? Why is Git? What does it even mean? Like, it's really weird. So let's ask Linus Torvalds, the creator of Git, like, what he has like going on there. So the name Git, according to him, was essentially like the name that he gave it in the README, which he described as the stupid content tracker. And it has several different meanings depending on your mood. According to Linus, the creator of Linux, the most commonly used operating system in the world. It means that's either a random 3-letter combination that is not pronounceable and isn't used anywhere else in Unix. It could be that. That's kind of like a very like mild-mannered, very serious Linus. This is the Linus, who created Linux right here. It could mean stupid, contemptible, and despicable. Just really upset about that. It could mean global information tracker because it's so good and everything works and like glory, glory, hallelujah. Or it could mean goddamn idiot, a truckload of shit, which is probably like the space where it is right now for all of you because you're all kind of like learning like how it works and it's really frustrating and you're wondering how is this like so like stupid and difficult to use. So yeah, no, it's okay. We've all been there. And yeah, I feel your pain. I mean, like, I don't feel your pain anymore because now, like, I understand Git, but I used to feel your pain. And one day you'll get there. Really, the best thing I can recommend for actually like learning how to use Git is to just use it. Just use it every day. Do stuff that like you're like afraid to do with it. Make up like make-believe projects and like play with it and try different commands. Just like put just like a little bit of effort into it. You'll eventually start to get it and be less afraid. Because like right now, like merge conflicts that like terrify you, right? Go ahead and like make some merge conflicts and solve them. And you'll see that it's not that bad. You'll get over it and like you will survive. But we're not learning to be users of Git today. We're learning to be creators of Git. We're going to make our own little version of Git. And I think this will actually benefit you all in the long run because by understanding the way that Git works under the hood, it will help you eventually when as you continue to use it and use it more. It is a tool you'll be using every single day. It's really just sort of the standard for most developers. There are other content trackers out there, but they're just like not as good. Like / opinion, I guess, but like Git is just like every single developer at some point or another uses Git. Like some people that aren't even developers use Git. That's far less common. But essentially, like basically get used to it. It's the only game in town, and it's the best game in town to play, as you'll eventually see. Its architecture itself is actually like really beautiful. Like I like it a whole lot, and it can inform your design of pretty much everything, right? So it's essentially like the way that it's structured is it's this very memory conservative, singly linked list that is incredibly intelligent and able to like handle huge amounts of data without like going totally like off the rails. It's really cool. It can also like right now it's a very complex area for all of you, so by kind of getting in and getting our hands dirty with it and like just basically like pulling out all the like the plugs and wires, can really demystify an area because probably like a lot of the reason that a lot of you are here is because you're kind of like me and that like you really don't like things to be magical. Like it's like I always feel weird saying this, but like I hate magic. Like I don't like not understanding how something works and feeling like I cannot eventually like get at some kind of like understanding for the way that like the internal of something works. And coming from like my last job, I was like a QA tester, essentially doing a lot of black box user testing. So like I never understood how anything worked, got really frustrated and decided to be a developer. That's like how I am here today. So doing this with Git, I feel, and for like anything that you ever work with, is always a good exercise. Death to magic. And of course, like knowing Git also will bring you nerd cred and like and many laudits from like other developers who have perhaps just been using it for years without wondering about what wonders lurk just beneath the surface. But cool. So let's talk about what a Git project looks like. So the most important part of any Git project is, of course, your project, right? It's the stuff that you're actually tracking. In Git terminology, we call that the working directory or the working copy. So this is just going to be everything in the directory that has your .git folder. Because when you say git init, what that will do is it will create a hidden folder called .git, which you can see just like any other hidden files that you have, like a git ignore or your bash rc or your bash profile. It will just like come into existence in your directories. If you don't believe me, then open up like any one of the projects you've been doing that you've been tracking with Git and type ls and then space -a, and you'll see .git there. It's totally there. So when you use Git commands, when you use the Git program that you've installed on your computer, Git is going to use the contents of that .git directory to change your working directory to match the way that it looked at a certain time when you committed. That's essentially like the core of how it works. We have a question up to the microphone.
Am I misunderstanding, or should it be inside of the Git directory?
Everything? Well, your working directory is everything outside of the Git directory, yeah. So your working directory is your project. So outside of the .git directory that's going to be where like all your project lives, right? Yeah. Sorry. Yeah. Sorry. Like slight word soup there, maybe. Yeah. So what Git is going to manipulate is going to depend upon what's inside the .git directory. Cool. So the .git directory itself, let's talk about it. It's not magical. Like we said, we hate magic and we want it to die. So, but when we use git init, that's going to create this Git directory that's going to right now contains all the magic, but we're about to explore it and dispel any magic from our lives. Let's do it. This essentially is what it looks like at sorry, dying. This is what it looks like in a broad scope, but there's a lot of stuff here we really don't need to care about. Essentially, this is all we really need to worry about for today. Let's go ahead and let's go and let's check out this Git directory right here. Or actually, let's make a new project. I'm gonna make something. Let's make a new project. I'm going to go ahead and make just practice project. Okay. So practice project. Right now, we've got nothing in there, and if I say ls-a, all I see are like the references to like going up like a level or two in my directory. So now if I say git init, then that initializes an empty Git repository just right there. So now if I ls-a, then I can see now I got this .git directory right there. Can everybody see this okay? Or is the color not so good? Let's can I do a new tab with, let's do this one right here. There we go, is this better? Cool, okay. Let's go into this .git directory and check it out. So we can see we've got all the stuff here. Remember, we don't need to worry about all of it, we just need to kind of worry about some of these things right here. And it's gonna become clear what they all do. So let's go ahead and the only thing that we have missing here for now is a file called the index, and that doesn't exist because we haven't done a commit yet. It doesn't exist until your first commit. We'll see how that applies. Sorry. Cool. So let's talk. So now we know how git init works. It just creates that directory with all of those files, and that's pretty much it. All it does is create them. So let's go on to so that's probably the simplest git command. The next simplest is probably git add. So that's something that we all know and love and use. It's just a two-step process, if I'm remembering correctly, just git add. The first thing it's going to do is it's going to create what's called a new blob object in our objects directory. So remember that a blob object is binary large object, and that's just going to be a compression of the contents of your file. So an object in Git, so when I say object, I'm not talking about an object the way that we talk about an object in an object in JavaScript, or even like an object in object-oriented programming. What I'm talking about is a little bit more in line of what we might think as like a document in a database or something like that. But here's what an object is very literally when we're talking about Git, is it's going to be a directory where the first two characters, where the name of the directory is going to be the first two characters of the SHA-1 hash of that file's contents, and the name of the file within that directory is going to be the remaining 38 characters in the SHA-1 hash. And then the contents of that file are going to be the binary compression of the file that you've made. Just going to be that's going to be the actual blob. So let's go ahead and let's do this. I'm going to make I'm going to get out of here first. I'm going to make test. I'm going to touch test. Oh dear. .txt. Or I'm not even going to use the txt extension. I'll just say touch test, and then I'm going to echo hello world into test. So now if I cat out test, we can see that it's just a text file with hello world into it. So let's do git add. Let's git add test. Cool. So now we have added that. So if what this has said is true, then what we can do now is we can go into our .git directory, and we're going to look for this directory right here, objects. Let's go in and check it out. Let's see what we got. Cool. So in objects, we've got these info and pack, which don't worry about. We don't need them. But we've also got 3b. Like, what the heck is this? 3b. So if we check out like 3b a bit, we can see that 3b is just the name of the directory, and what that directory contains is a file with this big long 38 character string, the 38 character string bunch of mess. Essentially, this is a SHA-1 hash of our hello world file. So if we go into 3b, like we can see, like there it is, and we cat out our file right here, what are we going to get? Who thinks we're going to get hello world? Okay, everybody, okay, nobody's falling for it. Now we're going to get a bunch of binary, like, gobbledygook. It's a binary compression, so it doesn't like being on the command line. But we can look at it using this special command called git cat-file-p. That's a cat filing its nails. So the P stands for patch, and what it allows you to do is it allows you to view the contents of a Git object. So if we go back and we git catfile-p and we give it a 3b18, that's probably enough for it to tell which one we want. So let's just do that. Then we're gonna see hello world. We're gonna see something that we want, not a bunch of gobbledygook. So we can see that this object that got created in our objects directory represents that file at the time that we used git add on it. Pretty cool. So it's right there, and it's there forever now. Pretty sweet. Cool. So that's step one. Step two is that Git adds an entry for that file in the index. So essentially, an index is just going to be a file where each line is going to contain the files that have been currently staged with their name, their hash, just a straight up list of everything that we have staged for a commit. And then we're going to use that index once we commit. So if we go back now to just the root of our .git directory and we ls again, then we can see that now we've got this new file here. We've got the index. So let's go ahead and let's cat it out. Oh no, we got gobbledygook again. Okay, so we're just gonna need another special command to get it out called git ls files-s, and that's a cat with a bunch of files. I really tried. This is, I'm bad at slides. This is my masterstroke, I think. So if we git ls files-s, where the S stands for staged, because we're looking for the files that are staged, then that's going to give us the contents of our index. We can see it's actually just a text file where we have these 4 columns. And they look kind of confusing, but they're not that bad. So we already know this last column, test, that's the name of our file. This middle column here is going to be the hash. And then these remaining two columns, let's demystify them. This first one might be familiar to you. It just represents the permissions of the file itself. This is it's just the file's permissions. If I were to change the permissions using chmod, then this would just be like a different value. You don't need to worry about it too much. This last one here, you're rarely going to see change. It's usually going to be 0. It's just called the stage, and this only changes in the event of a merge conflict. Because when you have a merge conflict, then the index will be in this temporary state where you have multiple versions of a certain file, in which case you're just going to have different copies of these files with the same name, and they'll just have different numbers for stage. So you might have like test from like my branch being like 1, and test from like Elliot's branch being like 2, and something. And that's just the way that Git tells the difference between the different files that are currently in conflict. So you won't even really see it unless you go ahead and examine it during a merge conflict. So again, the only the only ones we really care about here are the hash and the name. I'm not about to die, I swear. Even though it sounds like it. If someone wants to get me water, though, that'd be nice. Fellows, somebody, no, never mind. But cool, so that is git add. So the next thing, and the last thing that you're going to actually like create today, is a git commit, which is only slightly more complex. It's a 3-step process rather than 2 steps. And one of these steps is actually pretty difficult. In the workshop, I've done it for you. But it's not beyond you, it's just tedious more than anything. But feel free to do it yourself as well. So the first thing that happens when we git commit, thank you, is that we create a tree based on that index that's going to represent our project in its current state. So a tree is just going to be another Git object. It's just like the blob object that we created before. The only difference is that it's representing a directory rather than a single file's contents. So the content of the tree object is going to be a text file that kind of looks like this one right down here, where essentially we're just going to see a list of blob objects representing the files that are in that folder, and other trees representing subdirectories that we might have. We'll take a look at this in a moment. Yes?
Is that what the orange letters mean, like subdirectories?
Oh, no, the orange letters are just the syntax highlighting freaking out on this slide. They don't mean anything, sorry. Yeah, these orange characters right here, remember, these are just the permissions of the files.
Well, I saw it was like 2, it was 4 and then 2 and then none. It was like a tree structure. It's not that.
I don't think so, no. Yeah, this is just because because this is technically like a code block, and just the syntax highlighting doesn't know what to do about itself. So don't worry about that too much. So the first thing we're going to do is we're just going to create this tree that represents our entire project. And that tree is going to have either just single files in it, or it's going to have other trees. Cool. So then step 2 is we're going to create yet another Git object, which is going to be our commit object. And what the commit object has is it's going to have a reference to a tree, which is going to be the tree of our project root. So so back here for our practice project, the tree object that we put in the commit object when we commit in a moment is going to be the tree representing the practice project directory. And any other trees are going to be subdirectories that we might make. So the commit object is going to have that. It's going to have a bunch of other metadata too, like the author, the committer, and of course your commit message, which you should always have, because who doesn't want to talk about stuff? And then the last step is going to manipulate 2 of the other files that you may have seen and may have even just noticed as you have used Git, the head and the refs directory. So what we're going to do is we're going to In short, we're going to point our current branch at the commit object. And what that means is that we have this file called head, which is going to tell us what our current branch is. So if we look at the head file, that's going to contain a simple string just like this, and that's going to contain a file path, which is going to tell us which branch we're on. So if we go back here and we go into our Git, we can cat out head. It is in fact just a text file. We can see it's just pointing to ref/head/master, because the initial just branch on any Git project is going to be master. So essentially, it's saying if you want to know where to go to create the working directory for the master branch, then you need to go here. Like this is where you need to go. So then if we go to ref/head/ we're going to commit, so we're going to see how that works in a moment. It's not there yet, but we're going to say go here, and then in ref/head/master, that's just going to be like a very simple one-line text file that contains the hash representing our commit object, and we're going to just put the new commit object there. So that's a lot of stuff. It's a little bit easier to demonstrate rather than talk about. So let's go ahead. So we still got. Whoops. Yeah, let's get into our work tree. So we still got our test. Let's go ahead. Let's make a subdirectory. I'm going to call this subdirectory, just to be very literal. And let's go into subdirectory and let's echo goodbye world into another test. Cool. So now we got another test file that says goodbye world, and that is in a subdirectory. So right now our project looks like this. This is our project. We got practice project with a subdirectory and then another file called test. So let's just git add everything. So remember what that did is that updated our index. So if we let's go back to git ls files -s. We can see this is what our index looks like right now. This is what's currently staged for commit. We have subdirectory / another test. Important to note that it's the entire path right here, more than anything. This is what we have staged for commit, and we're going to have in our .git objects directory. We've got new stuff here. We've got new stuff for the objects that we've added. So now we're going to go ahead and we're going to make a commit. So let's go ahead and git commit -m. Yay, we are committing with that. Cool. So you can get some stuff right here. So let's go ahead and let's examine those different things that we've got. So if we go into .git/objects, then we can see we got quite a bit more stuff here. So we want one of these. Let's get cat file -p. Let's try. Oh dear. Oh dear. Let's try this one. Awesome, sweet. I got it on my first try. That never happens. Cool. So this is what our commit object looks like. It's just an object in our objects directory. So we've got this tree object right here. We have me, we have author and the committer, and we have yay, we are committing. So now we've got this tree. So let's go ahead and let's follow it the way that we would follow a linked list. Let's git cat file -p 3336. Cool. So this is a tree file that represents our current directory, that represents our project's directory. It represents the practice project folder. We've got another tree right here with its hash subdirectory, and then we have a blob for test. That's 3b, like we've already seen. So now if we git cat file -p 1d55, that's our subdirectory. Now we can see that it's a tree just like the one we just saw that just contains the blob. So if we git cat file -p 8b f5, then we can see it says goodbye world. Cool. So like everything is still there. Cool. Does that progression make sense to everybody? Any questions so far? Cool. So like the last thing to remember is that we created all those objects very wonderfully, and also the back into .get. So we got our head right there, ref/heads /master. So now if we go into refs heads master, into refs heads, and then cat out master, then we can see that is OA, and which OA83, which was our commit object. So this is the current commit that head is pointing to. So this is going to be what our working directory looks like right now. Pretty sweet. Cool. So now what happens when we git commit a second time? Because that was just committing the first time. That's kind of like a special case. We don't have like anything happening before. And the only difference when we commit a second time is that when we create our commit object, we're going to use the head to find what branch we're on, and then find the previous commit to the one that we're making right now. And we're going to add a new field to the commit object called parent, which is just going to point back in time at the commit that came before. So let's go ahead and let's just make a new commit. Let's go ahead and let's change test. Okay, let's go ahead and let's go back a little bit, and let's echo so long world into test. This is getting kind of a little bit grim. So now it says so long world. So if we can say git status, we can see that we modified test. That's not the same anymore. So let's go ahead, let's git add test. So that's going to create the new git object for it in the objects directory. And let's git commit -m changed test. Cool. So let's go ahead, let's find our commit object directly. Let's go ahead and cat out, let's change into our git directory, cat out head. So it's still going to be master. So let's go to refs, or let's just cat out refs heads master. So now we have EE3B. So let's go into our objects directory. We can see we got more stuff. We got more stuff now. So let's git cat file p EE3B. Cool. So we can see we've got our tree again, which is now D24B. It's different from what we had before. We still have our, so now we have a parent, OA83, which you might remember is the tree that we had last time. We've just put it here as a parent. So if we wanted to go back in time, we could find the parent to our current commit and go back. And we also got our message here. But now here's the cool part. This hasn't already been cool. Let's get cat file -p d24b. Cool. So what do we got here? We got test, and that's the one we changed, right? So if we look, we can see that its hash is now O2F5. That's not what it was originally. Remember, it was 3B. It was that was its hash before, but we changed it. So now we have a new object for it. But check this though. So subdirectory. We didn't change that on our second commit, right? So it's still 1D55. And if we go like back up to where we were before, remember we can see it was 1D55 right there too. It's the exact same object. We didn't create a new object for this subdirectory because we didn't change anything in it. We just reused it. We employed structural sharing and didn't like create a whole new thing. And that's kind of like that's sort of like the big reveal here. You know, that essentially like Git was smart enough to know that like, hey, I don't need to go ahead and like make a whole brand new copy of your entire project every time you commit. I just need to keep track of the things that have changed. So really, really intelligent, really beautiful, and now you get to do it yourself. It'll be a lot of fun. So let's really quick just go over a couple other commands that some of them are in the extra credit, and one of them is actually like at the crux of a capstone project. So you probably will not have time for it. That's git merge. But let's talk about branch. Branch is pretty easy now. It's only one step. All we do is we create a hash at ref/head/ the new branch name. So we've had master before. So now we might go ahead and we might point ourselves at a new, just like a brand new file representing our new branch, and we'll put our current commit hash right there. Now we know about it. If we want to switch back to the other one, then it will change where our head is pointing to. Pretty cool. When we check out, we just get the commit that the branch points to and ref/heads, and then we write the contents of our file tree to the working copy. This is like a little bit harder. Like a lot of fs write file happening here. We write those file entries to the index so that we could use them on a commit, and then we point head at the new branch. So again, pretty straightforward. You could do this yourself as extra credit. It's kind of fun. It's not that bad. This is that bad though. This is bad. Git merge. So git merge is tough, and depending on your situation, there are 4 different scenarios that you could account for, and this is just one of them. This is the simplest one. The case when nothing goes wrong. So let's go ahead and just talk a little bit about what goes on here, because Git is being pretty slick here. So let's say that we've checked out a new branch. We got a new branch here. We commit some changes, and now we want to merge those changes into master, and there are no conflicts. The following ensues. So we're on master. We git merge the new branch in. In this case, we would call master the receiver because it's receiving the changes from our other branch, and the other branch is going to be the giver. We're going to have 8 things that happen. Step 1 is we're going to write the hash of the giver to a file called mergehead. Step 2 is we're going to find the base commit, which is the most recent common ancestor between the giver and the receiver. So we kind of need to see where they diverged from. And then we need to generate indices for all 3 of these, for the base, the receiver, and the giver. Then we generate a diff between all of them. We just compare these indexes that have the hashes of their contents and see whether there are any differences there that we need to go in and examine. You're probably already lost because this is hard. I would not want to do this. Sorry, Capstone team that's doing this. Step 5, the changes indicated by the diff are applied to the working copy, and then the changes are applied to the index as well. The updated index is committed because remember, every time you do a merge, that also creates a commit. And this commit object will have 2 parents as opposed to just 1. It's totally fine. Because remember, when we had the nodes before, they might have multiple nodes pointing at them. But remember, that's fine because they have no knowledge of the nodes that point at them. Only those nodes need to care about it. And then the final step is that the current branch is pointed to the new commit. Okay. Let's not worry about that. It's a little bit more difficult. We just need to worry about doing git init, git add, and git commit today. That's going to be hard enough. Cool. But overall, though, in general, we can see that Git is pretty slick. It didn't do a bunch of wasteful operations. It kept its objects directory as lean as it could possibly be. The magic of hashing makes it really easy to tell whether something has changed in a file, even if it's as trivial as a bunch of white space. And by just changing references around, by changing pointers, we can save ourselves a lot of memory and just wind up with a really elegant data structure where nothing gets destroyed and we can always get our stuff back. So let's workshop. Any questions before we get started? No, who's ready to make this themselves? This will be sweet. Okay, so you're going to do another cool thing too when you get started is you're going to be maybe creating your first executable binary using nodes. That's pretty cool. You're going to be able to just type in fvs add and fvs commit into your terminal rather than saying nodes fvs.js or something like that. It'll be really cool. You'll feel super legit. Trust me, it's a nice feeling. So the spec is going to be in spec/fvs.spec.js, and then you're going to work primarily from fvs-your-work-here.js. Now there is a There's another file called FES.js. This is just helping. This is just helping the tests run. You're really going to be working out of FES your work here. It's going to be like this one right here. And the spec is fes.spec.js. Just make sure to fill in your name right here. That's going to be like the name that's going to be the author on the commit later. So it's just like important that you do that. Yeah, I could have made it programmatic, but I think I got lazy. So just like do it right there, and that'll be fine. But yeah, otherwise the only other thing to be aware of is, like I said, for the first step of commit, I've done that for you because it's tedious. So that's all in helpers.js. If you want to do that yourself at some other point, then don't peek. But otherwise, you are perfectly welcome to. Just you have been warned. Cool. So otherwise, let's go ahead, and we're quite behind, but that's okay. We still have an hour and a half to do this. So we'll do this until 5:30, at which point we'll have a review back here, and then you can all be on your way. So cool. Good luck, and remember, if you have questions, then just use the help ticket system. I am watching. Also, feel free to come up and just like grab me too. Normally that would be a no-no, but I'm going to give you all special permission. It's fine.
Do we need the functions?
No, they're not.
said it couldn't be done.
Oh, right, that was over here.
Is that so bad?
We got 30 minutes.
That's some cool graphics, man. You guys aren't allowed to look.
Oh no, idea stolen. Idea stolen. You guys should try to steal our idea and try to do it for us. Yeah. Get this board out now.
Is this the beginning of like working on capstone projects? Or when you guys are doing it now?
Yeah.
Move that chair, man.
I was like, this is gonna be hard getting this out.
Yeah, sorry about that.
Immutable chairs. Yeah, immutable.
I don't like the password banana meat. You didn't see the other one. You're right, I'm not sure I want to. We had one where we were talking about the Chinese motherland and everything. Oh, good. So this one actually came. My ism's get a lot less subtle than these.
Yeah, apparently.
Oh, you guys will learn that very well.
Cool. So hey, Elliot, are you good to go?
You need me to move my chair so you get out? Oh, you're going to hit the table.
This is gonna be a very slow process, so sorry if I'm bothering.
We good to go?
Bingo.
I'll take your silence as yes. Cool. Okay. So yeah, who had lots of okay, good. Cool. Who had fun? Everybody. I see everybody's hand raised. I'm just okay. Yeah. No. Okay. Sorry. Yeah. This is a really difficult workshop. Thanks for troopering. Troopering. I guess. Yeah. That's a word. That's a word now. Thanks for troopering through it. Let's go ahead and see at least. And I did discover in the middle of this that at least one of these specs is like definitely not perfect. So definitely we'll be sure to iterate on that for next time. But it's okay. It's good enough for now. But yeah, let's go ahead and let's take a look at how we might go about solving this. Let's go ahead and let's get started. The first thing I'm going to do, because I know to do it, is I'm just going to put aside a bunch of string constants for myself. Okay, and this is generally a good idea if you want to keep your code nice and dry, because I know that I'm going to have I'm going to use a lot of this stuff a lot. So I'm just going to go ahead and put all of my things into string constants, and I'm also going to introduce a template string if you haven't seen it yet. Which is using these backticks. I'm going to essentially compose a string right here in place. And this is going to be the same thing as if I were to concatenate the FVS variable onto the rest of this string right here. It's just a really nice way of interpolating variable values into a string. That's what the backticks does, and then a variable can be interpolated between curly braces and the $sign right there. It's really cool. Another huge 6 bomb, just dropping them all over the place today. Okay, so I'm going to make one for FVS, one for index, one for the objects directory. Whoops. There we go. That's going to be FVS slash objects. Let's have one for head, which is going to be FES slash head, and one for good old UTF-8, which I'm going. I forgot it's like this. Which I'm going to use in a moment. So we've also got all of these FS write file and read file things. And something I like to do, I'm just going to copy and paste some stuff here for a moment, is I like to, because I like functional programming so much, is I kind of like to just use a lot of small functions wherever possible. So I went ahead and let's see if I can even get it in here. No, it's going to yell at me. It's like, Tom, I don't like copying and pasting. I'm Vim. Okay. No, that's because I'm pressing that instead of, there we go. Sorry about that. Cool, so now I just have a bunch of tiny functions right here to wrap the FS methods for myself, just to make things easier on my life. So I've got my encoding, UTF-8 getting passed in, and I'm just making a bunch of simple functions called read, write, readdir, and makedir, so that I don't have to write out fs dot something wherever, everywhere, just making my life easier. I've also written them as arrow functions. Right here you can see. Arrow functions are really awesome and interesting, and I'm not going to go too deeply into them, but just know that these are just, in fact, just functions stored in variables right now. But definitely read up about arrow functions because they're not as simple as they seem. There's quite a bit of complexity to them. The only other thing that I'm going to make here is this other utility function called exists, which is going to take a directory path and a query. And what it's going to do is it's going to return true or false if that query exists in that dir path. So essentially, if like our dir path is, say, my directory right here, then I'm going to get an array of strings with like util.js, readme.md, and my second argument query might be like a string representing, like, let's say I pass in package.json, I would expect exists to return true in that case because package.json is going to be a string in that array. But if I were to put something like, say, like index.js in here, then I would expect it to return false because we don't have a file called index.js in there. So exists is just like a really nice helper function I wrote for myself. But it's yelling at me because we're not using any of these yet. So let's go ahead, let's fix that, let's do that. Let's use some of this stuff. So the first thing we've got here is create FES object. This is also, and because remember, this is a hard workshop, so this is one of the few that I actually generally go off my notes. I like to live code things as I go. But this one, like, I don't like to risk it. I don't know, because it is hard. But yeah, so the first thing we want to do is we want to get our hash. So I'm going to use I'm also going to use the const keyword as well, which is very similar to a regular variable using var. The only difference here is that with const, well, there are two differences. But the big difference that we're going to worry about for now is that I'm just using hash because that cannot be reassigned to a different value. So if I say hash equals like 1, 2, 3, I cannot later go ahead and say hash equals 3, 4, 5. This line will throw an error right here, where it wouldn't with var and it won't with let, which is another way of declaring a variable in ES6. So I prefer this because it's a little bit safer. And generally, I just like const. I don't know. But I know that I'm not going to need to reassign hash to be anything, so I'm just going to go ahead and make it const. Because then any developer looking at this will know it's like, hey, this is not a variable that's going to get reassigned at some point. That's a little bit more information that they can get just from reading the keyword. I like that. I like it when I can use the language that I'm working with to just give as much information in as little amount of space as possible. I like that. So what hash is actually going to be is it's actually going to be we have our get SHA-1 method again. We've got it. Whoops, I destroyed something. It's going to be up here. There we still got our get SHA-1. So this is going to be get SHA-1 of our file content. So that's going to give us that beautiful hash that we have before. So what we want to do, we know is what we want to do is we want to take that hash and we want to get the first two characters to be the name of our directory for our new Git object, our FES object, and the rest is going to be the name of the file. So I'm going to go ahead and I'm going to put them into variables as well. I'm going to say that like dir name is going to be hash.slice 0 to 2, and I'm going to say that file name is going to be hash.slice 2. There we go. Cool. So I got them right off the bat there, totally ready to use. So now we've got that. So next step is to actually go ahead and make this. Let's make a path for these as well, because what we're going to want to do is we're going to want to check and see if this already exists, and if it doesn't, then we're going to make it. So let's go ahead and just compose the strings that we're going to give to these functions right here. So I'm going to say const dir path, let's say, is going to be equal to two ways we could do this. We could just go ahead and say it's going to be, whoops, so we got objects, remember that's .fes /objects. So let's say it's going to be objects /our dir name right there. So really nice and composed. kind of like that. We can do the same with a file path. Let's do that as well. So we can, and like, see, like this gets like even more beautiful because we can just go right ahead and use that dir path. Oops. Uh-oh. Didn't want that there. And dir path slash our file name. There we go. Cool. Very nice, like composed strings. Very cool. This fills me with joy. I don't know if I hope it fills you with joy too. Cool. So now we got our file paths that we can use in these methods. So now let's go ahead and let's say that if not exists, I remember, so what the directory we want to check whether this exists in is going to be our objects directory up here. So I'm just going to go ahead and enter our objects string constant. That's going to be the directory that we want to check for the existence of this 2-character named directory, and it'll pass in the dir path, I believe. Fairly sure. Or no, we want the dir name. Sorry, because that's going to give us an array of strings representing the files or directories that are in there. Cool. So if that doesn't exist, then we're going to make dir with the dir path. There we go. Sounds like I'm saying dirt path, but I'm not. Cool. So now we can safely go ahead and we can write the file path with the file contents. Because if we were doing this like for reals, then we would want to like compress these file contents, but we're not doing this like for reals, so we're not going to worry too much about that. And then we're just going to return the hash, because that will be useful later. Cool. Let's see if I messed up. I'm not running the test, so let's mocha spec fes-w. And I need to actually first go ahead and go into my spec, go into fes. I've entered my name, but I have not removed this x right there. So that should definitely help. That will help us. Let's go back. There we go. Much better. Cool. So I already have my thing installed as global module, and I am just too terribly lazy to uninstall it. So that's automatically passing. But everybody got past that and had fun with that, I hope. So create FES object, that's working now. So now we want to create a blob object, which is just a very thin wrapper over create FES object. The only difference is that instead of expecting a file contents, it's expecting a file path. So all we need to do is we just need to read the contents from that file path. You know, so we might go ahead and say, go ahead and just get those file contents by saying read file path, and then return create FES object with those file contents. Let's see if that worked out okay. See if that is okay. Yes, that is okay. That is fine. Cool. So doing pretty good so far. Any questions up to this point? Yeah, I know. And something that's been like a problem for me with these specs actually is that this is like all this like so far without actually like doing any of the commands. I'd like to think of a way to get like around that, but we'll see. Maybe a future one. But yeah, so let's go ahead. Let's do what happens when we have to update the index. This is going to be some more string manipulation and like stuff like that here. I like these kinds of problems because they're like fun, puzzly sort of problems. I don't know. It's good for Code Wars. So the first thing we want to do is we want to what I suggest doing anyway is that you parse the index that you're getting here into an array, and that if it's empty, it should be an empty array. Because when we read it, we're just going to read it as a string from the file. So let's go ahead and say const index array is going to be equal to, so let's check and see if index is truthy or not, because it might be an empty string, and we don't want that. If it's truthy, then I'm going to say index.split, going to split it on the new line. Otherwise, I'm just going to make it an empty array, just like that. Because if I were to split it just like without thinking about anything, then I would get an array with like a little dud like null string in there, and that's annoying. Nobody wants that. But again, like I only know that because of like trial and error and having done this before. Yeah, yeah. Remember that like my speed going through this is not representative of like the speed you should expect from yourselves when like actually doing anything, because that's like unrealistic. You know, I'm looking at notes, so everything that's like, oh man, like Tom is so smart, he's just burning through this. No, I'm not. I've done this a billion times before, and like am looking at my solution. So don't worry. Don't like get like that like complex that like students get. I don't know, because I'm thinking of myself mostly, having a complex whenever like I see anybody doing anything really quickly and being like, it's like, oh, why can't I do something that like beautifully and magically? So yeah, digression. The next thing we want to do is we want to see does this file have that index entry? And if it does, then we just want to remove it. And I'm just going to be like really, and this is actually I think where there's a problem with the specs because I'm not checking it robustly enough. But what I'm going to do here is I'm just going to go right ahead and I'm going to take that array and I'm just going to do a filter. I'm going to filter each line. So on each line, if I'm going to split each line at the white space, because remember that what the index is going to look like is it's just going to be the name of the file and then its hash split by a space. So I can get into that space space right there just by splitting it. And then I can check the value of 0, which is going to be the file's name, and I can just go ahead and check and see if it is not equal to file path as the argument to filter, and that's just going to filter it right out of my array right there. So now I can go right ahead and use it the way that I want without even like really thinking about it. So what I'm going to do then is I'm going to go ahead and I'm going to push to it, you know, like, so I'm going to push this new entry, which is going to be the file path and the hash right here, and I'm just going to join it with a new line right there. I could have also used a template string here. This is the other way of doing it that I was suggesting earlier. Either one of these is fine. They're both like equally clever, but you know, just like a way of just quickly getting it in there without having to do a bunch of concatenation operators. So now it's there. So now I'm going to make that new index. So I'm going to just going to reverse the operation I did before, where I split it, and then I'm going to write to our index path up there with our new index. Just put it right back where I found it, and then I'm going to return it because my test wants you to. And let's see how we're doing. Not so good. Creates a new entry in the index. Oh, I assigned to a constant variable. What have I done? That is the beautiful. That is the totally intentional error that I meant to show you all right here. Remember, so like I said, constant variables cannot be reassigned. So instead, we want to use either var or let. I'm going to use let right here. I'm so glad that I cleverly thought ahead of time to run into that error. Cool. There we go. All right. Awesome. Check how we're doing for time too. Oh, cool. We're pretty good. But that's all the helper functions, and they're probably like the hardest part of this whole thing, I think. Perhaps a little bit unnecessarily so. Again, still always a work in progress. So let's go ahead and let's actually like do like the commands that are going to be like fun. Let's do them. Okay. So init, pretty straightforward. This one not going to be so bad. So the first thing we want to do is we want to check and see if an FVS directory already exists. So we can just go right ahead and so let's say if exists, and we'll pass in, and we're going to check our current directory right here, and we're just going to check for FVS, which we have stored in our string constant from before. And if we do that, we're going to throw a new error called no file name specified. Cool. So we're going to throw that error if that's the case. I think that's pretty good. So now we just need to make all the stuff that we need to make. So this is actually like a little bit tedious, and I can't even, because it is tedious. I'm just going to copy and paste it. Sorry. Let's see. There we go. Cool. There we go. So we're going to just make FES. So remember, if we go back upstairs right here, we've got all of our string constants, just the paths to the ones that they're referring to. So we're making FES first, because that's kind of like a dependency for all the other ones. Making objects, making refs / master. I probably could have dried this up a little bit, but I was bad. And then we're writing, and then head, we're putting that in ref / master. Remember that in real Git, it's ref / head / master, but I just took out heads because we don't really do anything with that, and I wanted to make it a little bit shorter for everybody. You're welcome. But cool, so that should be okay, I think. Let's see if that's okay. How are we doing here? Throws an error if already exists. If exists, FES, throw new error. No, oh, no file name specified. Yeah, okay, that's wrong. That's because I was looking ahead. .fes already exists. There we go. That's what we want. Sorry. There we go. Beautiful. Cool. Let's do add. Let's do add. Cool. So first thing we got to do is we got to yell at people if they don't use our program correctly. First and foremost on everybody's mind, I'm sure. So let's go ahead and let's see if we have the file name that we're adding, because remember, we're going to say FES add and then some file name. We're going to just like add the file. So we get that off of process.argv.slice2, and then it's going to be at index 1 of that sliced array. Just something that, just kind of like hearkening back to, like some, I guess like maybe like a couple weeks ago, maybe like 1 or 2 weeks ago. Everything moves so fast. If we don't have that, if we didn't pass in that argument, then we get to yell at people. We get to say throw new error, no file name exists. There we go. That's what I wanted before. So now we can yell at people if they don't pass in a proper file name. Cool. Is there a question or? Are you?
We were just trying to get the code to work.
Oh, okay. Sorry.
Sorry about that.
Yeah.
I think it's no file name specified.
No file name. Oh, specified. Oh my goodness. There we go. Much better. Okay. Cool. So now what we want to do is remember that when we add, that ends up creating the index. So if we don't have one existing, this is like the first thing we're adding, then we're going to need to create that index. So let's go ahead and say if not exists in the FBS directory, if a file called index doesn't exist, then we're going to write an empty string to index, just like that. Cool. So that happens now. So then we actually have now, so that with all that throw clearing out of the way, we can do the actual two-step process that we do with git add. So the first thing we do is we're going to create that blob object, which is now going to be quite easy because we did all the heavy lifting. So we can just go ahead and we can create blob object from the file name that we've gotten in from process argv. We just go ahead and we can create that, and then the second thing that we do is we need to add it to the index, which again we've already done so much heavy lifting there. We need to put in the index. So let's go ahead and let's just like read from the index and add that as the argument to update index right there. The second thing is going to be the file path, which we have right here with file name. And then the last thing is going to be that hash, the blob hash right there. Then we can just go right ahead and return the hash. Let's see how we are doing. We're doing pretty good. We're doing good. The last thing we got to do is commit. And with commit, one step is already done for us because essentially what this step is right here is it's creating that all those tree objects that otherwise would be like very tedious to do. because like imagine it would kind of like you basically have to recursively go through like everything and do a lot of really annoying string concatenation, and which may be fun like like Monday morning during like a code wars, but at like 5:30 on a Saturday I figured I would spare you all. So but here it is. So when you are refreshed, maybe give it a go. It isn't it is fun, but yeah, like it would have been maybe more suffering. So so I did it for you here. But yeah, so we got that out of the way. So second thing we want to do is we want to create this commit object. So let's go ahead and let's do that. So let's see. So let's think about the things we're going to need. So we're going to want to need we need an author, right? Let's start with author. That is of course yours truly. So I'm just going to hard code my name right in there because that is what that's what I did back here. My name, Tom. Let's just hard code my name right in there because I felt like it would be just like too much to do it programmatically, even though it would be like an extra line of code, I'm sure. So we've got our tree root hash. So remember, we need a line with our tree. So let's go ahead. Let's put that string into a variable as well. I'm going to go ahead and say that that's going to be tree, and then tree root hash. There we go, right there, just like that. Right. And then let's see. So we're going to need to. Oh, and we need our message as well. Yeah, we need our message. So our message, remember, is coming off of the commit. It's coming off of the arguments that we're passing to commit from the command line. So that's going to be on process argv as well. So let's go ahead and let's do, let's say const message equals process.argv dot slice to 1, and then if not message, we're going to throw a new error once again, no commit message. How could they? How could they? Cool. So that looks pretty good. So now we got our message. Message is just going to it's just gonna be equal to message, right? Let me see. I didn't even do anything special with it.
The process.argv, is that just a node thing?
Yeah, totally. So remember that with your node process, you have this global variable called process that's going to be available in any node process, and that has a lot of various interesting stuff there. Probably the most thing that we're interested in is the argv, which is going to be the arguments that are passed in to that process from the command line. And we need to slice it a little bit because if we were to go ahead and let's take a look at process.argv, then we're going to run into a syntax error because I cut this off in the middle of something. There we go. Actually, you're getting my mock things right here. Actually, not like a real thing. Let's go ahead, and I'm going to just really. There we go. Cool. So really quick, that's just a simple JS file that's console logging out process argv. So we can see we just get an array of two things. We get the path to our node binary, and we get a path to the file itself. So that's why we're slicing it too, because we don't care about these things. Node cares about them, but we don't. We care about the arguments that are getting passed to test.js. So if we were to say something like node test.js hello, then we can see that hello appears as this argument right here. So if we do console log it out right here the way that we'll actually use it, then we'll see that the arguments that we're going to get is fes commit, which is the command that we're doing, and then the message, say commit testing. Or if we're doing add, then it would be we're not going to see it because I'm logging it inside commit, but it would be fes and then add, and then the file name that we want to add. So that's how we're obtaining our arguments. Because eventually in the real world we would be saying fes add, the argument right there. But cool. So that's how we're doing that. Let's get rid of that before I forget about it. Cool. Cool. So where were we? got our message, we got our index, we got the author, and we got the tree. So this is going to be fine for our first commit. But remember, our second commit also needs, and all commits subsequently need this parent, right? Which is unfortunately syntax highlighted differently because some programming language somewhere has parent as a keyword. So our parent, remember, is going to be the previous commit, which is going to be stored in the file that head is pointing to. So let's go ahead and let's get that. So let's see. So we know that our current branch. So let's say current branch is going to, if our current branch is going to be like .fes slash, and then if we add so if we read from head, so remember the head, when we initialize it, is just going to contain this path to refs master. So what we want to do is we want to read from fes slash refs slash master. And I think in the code I pasted from this is wrong because that should, or no, that shouldn't contain anything, that's fine. We're going to want to copy from fes slash refs slash master. So I'm just composing that really quickly here. That is the string representing the path for our current branch. So let's see. So if we want our parent commit, so like parent commit is going to be, we're just going to read from our current branch, and that's going to give us either the hash for for an existing commit, which will be our parent commit, or it'll just be that empty string that we put there before. So let's go ahead and let's think. So let's actually start to compose our commit object, because remember, it's just going to be a text file that has all this information in it. So we can go ahead, we can put these into something like an array, and just join that into a string, like the way that we did before. I like to do that, so let's go ahead and do that. I find it's like a nice way to like make like multi-line things, just because you don't need to like do like weird concatenation stuff. So let's go ahead and say that let's let our commit. So let's see, we know that it's going to have, these need to be a certain order too, I think. So I'm just going to check. We have our tree, and we have the author, and then we have the message. There we go. So this would be what we wanted if we didn't have a parent commit, and we need to be able to handle both the first commit and all subsequent commits. So let's go ahead and let's check and see if the parent commit is truthy, because remember, it will be an empty string. If this is our first commit, there'll be nothing there. So if parent commit, then let's go ahead and say, let's just go ahead and push parent commit into our commit array right there. We'll just go ahead and do that. It also needs to be, before I forget, it needs to look something like this. Parent commit, there we go. It just needs to say parent before it, the same way that it says in Git. So that's going to be in there if we have a parent commit. Cool. So let's go ahead. So let's go ahead and let's go ahead and say that our commit like string is going to be commit. We're just going to join it with the new line. And then we want to create an FBS object for it, right? Because we got this commit, and it's going to be an object on its own. So let's go ahead and let's get the commits hash by saying create FBS object and pass in the commit string. Pass that string in, it'll turn it into an FBS object, and we get the hash afterwards, so that we can just go right ahead and return commits hash. Cool. I'm missing one thing. Yeah, we need to point the current branch at that new commit object. So So let's go ahead and let's write. So we've already got current branch, which is fes/ref/master. So let's just go right ahead and let's write to current branch, and let's just give it the commit hash that we got. There we go. Write commit hash, and then we can go ahead and return this. And that causes everything to pass. But let's not take my word for it. Let's go ahead and let's play with it. So let's go ahead and let's go into our, not that one. I want, which one do I want? Practice. Oh, did I already get rid of practice project? I think I did. So let's go ahead and let's make dir practice project only. This time, instead of using git, we're going to use fes. Cool. So let's say fes init. So, oops, it is a hidden file, so ls-a. Cool. So let's go into fes. We've got our head, our objects, our refs. Pretty sweet. Let's make a file. So let's make hello world into like this file called hello. And let's fes add hello. Cool. So now if we go into .fes and into objects, we can see we got 22. So we can see that that's all there in 22 now. So if we cat out 5.9, if we cat this out, we can see that it says hello world, the way that we did before. And we can see we got the index file there too. And we can see that there's not a new line at the end of it for one thing, but also that otherwise it looks pretty much the way that we'd expect. So that's pretty cool. So last but not least, let's fes commit with nothing just to make sure that we get an error message. Isn't that nice? For yelling at us. Let's make a message saying my first message, because it's not smart enough to recognize spaces yet. So that's extra credit. Make it like actually smart enough to handle quotes and things like that. But yeah, so now let's go ahead into fes. Let's go into objects. We can see we got 22, we got 3a, and we got f4. So let's go ahead and let's check out 3a, which is going to be this one right here. No such. Oh, whoops. I want to actually. Whoa. It's mad at me. 3a. Yeah, let's do that. There we go. Cool. So we can see that's our tree. So it's ls again and cat out f4. There we go. So now we got our commit object right here with the tree 3a, author me, my first message. I need to npm install -g again because it's still using Tom Kelly instead of Tom. Let's cat out 3a. See, that is our tree, and then that's going to be hello world. So cool. Seems to work. So let's like modify. Let's echo goodbye world into hello. Let's fes add hello and fes commit second commit. Oops. Cool. So let's check out our head now too. So that's still gonna be ref/master. So let's cat out ref/master. So that gives us 3D80. So let's go into objects, and there is 3D. So let's cat out 3D. So we can see there's our second commit with our second tree. So let's cat out our, it's actually getting hard to see. 1 second. Cool. We got our second blob for hello, and when we cat that out, we get goodbye world. So we have a very basic functioning Git clone right here. Not recommended to use in your own personal projects, but you can see how like we could eventually add more and more features to this and potentially like even get it working nicely. So pretty cool. It's definitely, and some like Git is like an example of probably one of the most used like the most used, most famous pieces of software in the world. You can see like how like it's not really beyond you. Like even at this point, this is a difficult workshop, like obviously, but it's definitely nothing that you can't go for yourself. So I always think that that's like a nice thing to carry away from this workshop. That like even like really complex, really incredible things like Git, you can totally do. And if nothing else, you can at least npm install globally a binary and like make it look like super legit, at least. That's pretty cool. Cool, slightly over time. So maybe like any like final question before we break? Could Mike, sorry.
It's not really a real question. Could you just go back to the commit code for a second?
Oh. Yeah, this right here.
Oh,
Oh,
okay.
yeah.
I think you just missed a line or two.
Did I? Yeah, it is there. But cool. All right. So happy Saturday, everybody. Have a restful tomorrow, and we will see you all next week. Have a good weekend.
Thank you.